5 minutes. It will be like 30 minutes plus 5 minutes. So I request all the speakers to please limit their presentations, okay, within 30 minutes so that we can have discussions for about 5 minutes. And we'll have a break in between. So the first talk will be given by Mark Tuckerman from New York University. He's going to talk on using machine learning to process high dimensional free energy surfaces into low dimensional paths. Mark, please.
Thank you very much, Amalendu, and thanks to the organizers for inviting me to this meeting. Let me grab an annotator here so I can actually have a little pointer. Good. So it's really a pleasure for me to be able to talk about the work that we've been doing. I will say at the outset that we didn't quite get to, let's say, the killer application where I can show you an entire workflow of first generating a high dimensional free energy landscape and then being able to pick 2 points on it and actually study pathways between two interesting basins. But what I want to try to show you is what the different pieces are and where, we're employing things like machine learning and techniques like this to help us find pathways between interesting states. And I'm going to do this in the context of crystalline systems, so atomic and molecular crystals, which is where we've been focusing a lot of our efforts of late. Although we are starting to do some of this also for peptides as well, but I think given the length of the talk, I don't really have time to get into that today. So maybe at the next rare meeting, I'll have more to say about that. The reason I wanted to focus on crystalline systems is that I think in the context of the rare meeting, these remain among the most challenging of the rare event problems. And there really is a lot of work for us to do to be able to understand, especially molecular crystals, where you have lots and lots of molecules that may be highly flexible, and your crystals may be in non-orthorhombic space groups, and you might have high Z prime numbers and things that are really challenging industries like the pharmaceutical industry. All right, so this is an area where the kinds of simulation techniques that I'm going to be talking about are really just beginning to break through. What is our motivation for working on these systems? Well, I mean, one of the most common ones is polymorphism in the context of pharmaceuticals. Now, just to remind the audience, polymorphism refers to the ability of a compound to form multiple crystal structures. And why is this a problem and possibly an interesting thing to exploit? Well, let's first start with an area that, where this really is a very significant problem. That's in pharmaceuticals. And although everyone likes to talk about ritonavir and the AIDS drug, I'm going to talk about this drug rotigotine, which is actually used to relieve symptoms of Parkinson's disease. Now, the way this works is you form a molecular crystal with this molecule, and you grind the crystal into fine particles, fine crystalline particles. And in this case, instead of forming a tablet, you spread the particles over a patch, you apply the patch to the skin, and then the skin absorbs molecules from the surfaces of these tiny particles, presumably from surfaces where the extraction free energy is relatively low. Now, in the case of rotigotine, the pharmaceutically active crystal form is this one that you see on the left. This is now known as form 1. And it was used to make these Nupro patches. But it turns out that if you let these patches sit around, you actually start to see these snowflake-like patterns appear on them. And this is signifying that you actually have another crystalline form appearing. This is now called form 2, all right? And often the way that this happens, if it's not spontaneous, is you have a little seed of a contaminant, which in this case is the wrong crystal structure, getting into your manufacturing process somewhere, and these seeds get into the crystalline form, and it causes a conversion that may happen on a very slow time scale. Well, it turns out that these new crystals that are forming on the patches are very stable, and so they're no longer absorbed by the skin, and so this becomes pharmaceutically inactive. In other words, the drug fails. All right, and when that happens, you have to recall your drug and you have to try to find a way to reformulate it so that you avoid this late appearing polymorph. Well, it's been estimated that there could be as many as 15 to 45% of pharmaceutically active compounds that have these late appearing polymorphs. And this is something you'd like to know about before you go to market with your drug, obviously, because if you catch it too late, then you take the cost and the PR hit of actually having to do this massive recall. Well, doing the experiments and try to find all these polymorphs can be difficult. It's time consuming. It's usually expensive. And this is an area where computational methods are sort of poised to play a really important role. But let me point to another area. This is much less known, but it turns out to be extremely important. And it has to do with contact insecticides. Okay, so my analogy for this is here's a guy walking on these beautiful crystals in a mine in Mexico. These are giant gypsum crystals. And so I call this guy a crystal walker. All right, and that's sort of a metaphor for what happens with the kinds of molecular crystals that are used to form contact insecticides. Now, DDT is an old insecticide that's been long banned, all right? But it was an interesting playground for some of the experimental groups here at NYU. Same idea applies. You take the molecule, you form a crystal, you grind it up into these small particles, and in this case, the insect walks on the particles. It absorbs the molecules through the feet or the tarsi, and they go into the insect body and shut down ion channels or whatever they do to kill the insect. Well, when DDT was used, the commercially available form was this one called Form 1. Well, my colleagues at NYU recently crystallized a new form of DDT. It's called Form 2, and it's a metastable polymorph, all right? So in this case, they're exploiting polymorphism to try to find something that may be more lethal to the insects. And in fact, you can prove that this is a more effective way to deliver the exact same compound, but in a different crystalline form. So what they did was they took fruit flies and they ran 3 trials for the Form 1 and for the Form 2. And of course, there's a control group that's not being exposed to anything. And when you watch the exposure of these fruit flies to the different crystalline forms, you'll see very clearly that those that are exposed to this Form 2 crystal are actually being killed faster than those that are exposed to Form 1. So you're delivering the same compound, but because you're delivering in a different form, you get something which has different properties. And in this case, the lethality is actually better. You can quantify this by showing, what we call lethality curves, or the fraction of flies killed at over a certain period of time. The 3 black curves here are the Form 1, and the 3 red are the Form 2. And you can see, the change or the more rapid rise time for the Form 2 crystals. All right. So this suggests that you could actually use less of the toxicant to better effect, meaning that you get more of it absorbed. And this has a kind of favorable environmental implication, right? Because if you're targeting or if you're more effectively killing your target, then the side effects of, let's say, killing honeybees or things like this will be reduced, as well as the amount of runoff that you might get of this toxic compound. So everyone knows the Ostwald rules of stages in crystal formation. The least thermodynamically stable phase is the one that forms the first. And you can imagine a corollary on lethality of contact insecticides, which is that a metastable or thermodynamically less stable phase is one that's going to be more lethal or kill the fastest. Okay, now DDT, as I said, is no longer used. So let's talk about a compound that actually is currently in use, Deltamethrin. And so again, the commercially available form is this Form 1, and my colleagues crystallized this other form called Form 2. You can see it's in this non-orthorhombic space group. And when you compare its effect on the Aedes mosquitoes, which are, I think, the ones that carry dengue fever, you can see that Form 1 has an okay rise time, but Form 2 really is quite dramatic in this case. Now, unfortunately, mosquitoes are growing resistant to some of these indoor sprays, right, like Deltamethrin. And this was an article that came out in Science last year, and it suggests that with this growing resistance, you need to be able to switch compounds and be able to find these interesting polymorphs. And of course, in their hands, they're very good at this. So my colleagues use this melt recrystallization technique. And in fact, for this compound here, imidacloprid, they've been able to find a whole slew of new polymorphs. So I think 1, 2, and 3 were known, and then they've generated polymorphs up to polymorph 9, which is the one you can see down here. And if you look at their effect on a variety of mosquitoes and fruit flies, you can see that, again, you know, the form 1, the commercially available form is okay. But if you look at these different polymorphs, especially polymorph 9, the rise time of these lethality curves is really dramatic. So it's a dramatic improvement just by exploiting this concept of polymorphism. Now, what's interesting about these crystals that you see here is that, you know, there are different conformations of the molecule that you get in different crystal structures. And it turns out that the form or the conformation that you get in different crystal structures is not necessarily going to be the gas phase minimum for these internal dihedral angles. So this is a gas phase potential energy curve of the dihedral angles. And yeah, some of the crystals have these dihedral angles at the gas phase minimum, but some of them clearly are up the wall, right? They're not. Well, this is an example of the crystal form stabilizing conformations that are not gas phase minima. And these are very hard to find when you're doing crystal structure prediction. So let's talk about how we actually use molecular simulation to explore crystal structures. And in fact, what we do is we use collective variables that are kind of designed to distinguish different crystal structures. For example, the cell shape, all right? So the 3 cell vectors, these could be different in different crystal structures, all right? Orthorhombic versus non-orthorhombic and different lengths and so forth. What about the molecules? All right, so one possibility that comes from the work of the Parinella group some years ago is to use a kind of entropy created from a spatial distribution, which we just model by a set of Gaussians in distances between pairs of molecules and angles between them, all right? And you can see that if you drive the cell and this entropy variable on this urea crystal, you can actually get this thing to explore different polymorphs on a free energy landscape characterized by these different collective variables, okay? You can also use packing parameters like Steinhardt parameters, which are good when you have, you know, a central unit and then units around it. And these are good for, again, finding, you know, different angular patterns. And although I show it here for an atomic crystal, you can actually create molecular analogs of these by using symmetry related atoms and their centers. And you take these as the vectors that are used to construct these angles and distances. Okay, and that's actually, and then on top of that, you might have to use, you know, internal degrees of freedom like these torsions. So you have a fairly high number of collective variables, and you want to explore the free energy landscape as a function of this very large number of variables. Now, when it comes to rare event sampling, there aren't that many methods that can explore very high dimensional free energy landscapes. And I think in the next talk by Nishant, we're going to hear more about that, or not the next one, but the one after Ron's talk. But let's talk about how we actually explore these free energy landscapes. So let's suppose you've identified whatever set of variables that you want as your collective variables. So say there's little n of them. And the problem that you have to solve is to calculate this marginal probability distribution, which is an integral over the phase space of the Boltzmann factor of your Hamiltonian. And then you have these delta functions that say these collective variables should have certain values. And if you can map out this function in this n-dimensional space, then the negative log of it is by definition the free energy landscape. All right, so I think we're going to see this formula a lot probably during this conference. Now, of course, if you want to try to map this function out on an n-dimensional grid, you'll find that for n more than 1 or maybe 2 if it's a real true to force calculation. Your ability to do that, it just becomes extremely difficult because of the dimensional explosion. So the way you want to approach this is to try to sample this marginal distribution. But how do you sample a function whose form you don't know? Well, we're going to do that in a kind of on-the-fly technique within the simulation. So the first thing you would do is to take these delta functions and replace them by Gaussians that are, designed to be very, very narrow and highly peaked. And when a computer, they look a little bit like delta functions. But if you write them this way, then you can take this exponential and fold it into your Hamiltonian. And when you do that, it looks like a kind of harmonic coupling between the collective variable and the S that characterizes your marginal. So the way that you would sample something on the fly to sample this marginal is to extend your phase space, treat this as an additional kind of potential energy term, and add a kinetic energy, a fictitious kinetic energy with some fictitious masses for these S's so that you can actually move them around, all right? Now that'll sample something, but it doesn't actually sample your marginal until you include some additional conditions. And the most important one is an adiabatic decoupling between the fictitious variables and the physical variables. You want to make these S's very heavy compared to your physical variables. Now that will sample the marginal, but it will do so very inefficiently. So the way that we boost the sampling is to introduce a temperature for these S variables that's large compared to the physical temperature, large enough so that you can cross any barriers on your landscape, okay? So your equations of motion for this kind of adiabatic dynamics looks like this. Your physical variables are at physical temperature, and these extended variables, which are just governed by this harmonic potential or harmonic force, are at this high temperature. So let's imagine this is your rough energy landscape and you're going from this basin to this basin. What these equations of motion do are they allow you to cross the barrier easily. So you're sweeping over your free energy landscape. And as you move around it, you're generating more and more information about the free energy surface. What you can prove is that if you take a histogram of these S's, you'll get a marginal distribution called the adiabatic marginal that's related to the true marginal by a power that's the ratio of the two temperatures. So you can see that if you take the log of both sides, that brings down the T over TS factor. Or then you can multiply by KTS, the TS's cancel. You have KT log P. That by definition is the free energy at the physical temperature. Okay. Now we can compare this scheme that sweeps over the free energy landscape to the popular metadynamics method, which is a bit more serial, right? Metadynamics basically fills a basin with Gaussians that you place down there on the fly. Once you fill a basin, you cross over to the next one, you start to fill it. And as you sum over all these Gaussians, you generate the free energy, okay? So you have to go from basin to basin. The advantage of being sweeping over the landscape like this is, one, you can use a very large number of collective variables, and two, as you generate more and more information, you can combine this with machine learning, all right? So as I get, let's say, a sparse scattering of points, I can feed that into a neural network and I can train it. And then, since it's a regression network, it should be able to fill in the missing information for me. So this has actually been very useful for us to run kind of short simulations and then use the machine learning to fill in the missing information. So let me show you an example where we're generating a polymorphic transition in a crystal. This is resorcinol. And it turns out resorcinol has a number of low energy polymorphs that are these three red ones and this black one down here. Now, these are conformational dependent, like our imidacloprid. So the three one up here, the epsilon, the beta, and the P21, are created when these OH groups are in this cis-like configuration, whereas the alpha polymorph has them in this the cis-like configuration. This is trans, this is cis. And of course, the trans configuration is the gas phase minimum, not this one, all right? But this happens to be the lowest energy polymorph, lowest free energy polymorph, all right? And to know that you're getting the right, crystal structure, you can compare PXRDs. And if your force field is good, then you get this kind of match. So you know that you're getting polymorphs that are experimentally realizable. Now here's a simulation that shows that when I start off in one of these upper polymorphs, in this case it was the beta polymorph, and I use the let me come back into this slide. And I use the entropy and the cell variables as my collective variables. And I can actually generate a polymorphic transition from, in this case, beta to alpha. All right. And that has to undergo an internal conformational change, right? So you see that you go from this trans configuration to the cis configuration. This is actually the first time someone's been able to generate this particular polymorphic transformation. And we can get this by starting either from the beta or the epsilon or this P21 polymorph, and it will always go to the alpha one. And there is a large barrier to doing that along this particular trajectory that we have. And you can turn this into a set of free energies at the end of the day, all right? And they're all relative to the alpha polymorph. And you do this at different temperatures, all right? At 0, it's just the energy. But at finite temperature, it's a free energy difference. And the ordering is alpha, beta, epsilon, P21 at most temperatures except the very lowest ones, okay? So we have a set of free energies that we get from a landscape. And what we would want to do is to be able to say, pick 2 of these polymorphs and somehow get the kinetics of the transition from one structure to another. That way, you know how metastable a particular polymorph is, and could you use a metastable form for some application? All right, we haven't been able to do that yet for a molecular crystal, but I do want to show you how it works for a simple atomic crystal. All right, so this is another piece of the puzzle, and this is another area where machine learning becomes important. So let's suppose in this case, I have an atomic crystal and it's molybdenum, and I'm interested in the transition, the polymorphic transition between a metastable phase. In this case, it's this A15 phase shown in red, and the more common BCC phase. Now, the A15 phase is actually a phase that's used in molybdenum for spintronic memory devices. And of course, the BCC is used for electronic applications. And it turns out that, A15 is metastable and can convert to BCC on some time scale. So it's not enough to know that these phases exist. What we want to know is what is the barrier to the transition between one phase and the other. Now, if you just run a molecular dynamics simulation, just straightforward MD with an interface between them, which is one way that you can get a polymorphic transition to go, you can see that this is a very, very slow process. All right, and maybe you get a couple of layers to transform from one phase to the other. Now, it turns out that finding collective variables for this particular transformation is extremely difficult. None of the ones that I showed you will work for this, all right? Of course, we know that the difficulty with this problem is, the rough energy landscape problem, but it doesn't mean that I automatically know what the right collective variables are. This is where machine learning turns out to be really important. So let's suppose you've done some kind of, let's say, exploration of the landscape, the free energy landscape of the different phases that you have. So you can use collective variables that I showed you to do that, but it won't get you the right kinetics. So in this atomic crystal, we have the usual phases of HCP, FCC, BCC, and A15. What I want to do is to be able to find a kind of a path from one phase to another through some mechanism. Now, lots of polymorphic transitions may occur on surfaces or at local nuclei or seeds or at interfaces like we have here. So what we're going to do is we're going to use local information in the crystal in order to find a set of descriptors for a machine learning method that can classify these different phases. And a common set of descriptors are those that are used to make neural network potentials. These are the so-called symmetry functions, and they're useful here because they are translationally and rotationally invariant. So, for example, we have these Gaussian types where you can tune by this parameter RS where the center of the Gaussian is, and this will be sensitive to maybe the first solvation shell or the second coordination shell of a given atom. Or you have this one, which is similar, but it has a sign that you associate with different regions of your crystal. So once you have a set of, you have a set of descriptors. These are distance space. You can use the Steinhardt parameters for angular information. Once you have a set of descriptors, what we're going to do is to train a neural network to classify the phases based on local structural information. Okay, so by giving it lots of examples of different environments, I can have it spit out for me a probability that a given configuration is in one of the various phases that we have, including mixed phases like interfaces. All right, so here's an example of an interfacial configuration. And what I do is I take these local classifiers, these local probabilities, I average over all the atoms in the cell, and I create a global classifier for a simulation cell that may be pure or may be mixed. In this case, this is the same snapshot showing you BCC and A15 at an interface that may contain other structures. So for example, the global classifier for BCC shows 0.2, and the A15 is 0.52. They don't sum to 1 because you have other stuff in there. Okay, what we're going to do now is we'll train the neural network using a bunch of configurations that are generated from MD at different temperatures, as well as enhanced sampling to get me mixed phases. All right, so I can use all those collective variables that I showed you for the enhanced sampling just to get data for my neural network. All right, and so this is an example of a enhanced sampling simulation of an atomic crystal. It's not molybdenum in this case, but I can generate, let's say, a free energy landscape, and I can see different phases that appear there. And I can use all that information to give me environments for my neural network. Here's my neural network architecture. I've got 11 symmetry functions and 3 Steinhardt parameters, 14 descriptors. I have 2 hidden layers with 25 nodes in each layer, and then my 5 outputs. And of course, because it's a classification problem, this is the cost function I'm using. So that's my neural network. These are the target values. And then you create a test set by siphoning off 125 additional environments, and you get a learning curve that looks like this. And you can see that, you do pretty well for all of the pure phases. So all the different, the 5 phases, and these, this includes disordered phases that we call liquid phases. And then those that are interfacial, mixed phases, it's a little bit harder to get good classification, but even here, the error is less than 0.1. So we have about 94 to 95% classification accuracy, even for the interfacial ones. So then what we want to do is we're going to pick 2 phases that we're interested in, 2 polymorphs. All right, so in this case, it's A15 and BCC. And our collective variable that we're going to use to generate the path between the 2 phases is what we call a path collective variable. All right, so we were inspired to do this by this early work from 2007 of the Paranello group, where they did this in configuration space. We are doing it in the machine learning space, or the space spanned by this classifier vector. All right, so the QI are a set of nodal points that march from one phase to the other. All right, and then what this variable will do is it will sample paths that are foliations of the nodal points. All right, so you'll be able to distort this along directions perpendicular to the line, and you can create different pathways. All right, now this may be a little bit unrestrictive, so we also add in, this orthogonal variable to create a sort of penalty if you get too distorted. Right, and we add that in as a second collective variable or a bias. All right. Now, the reason for working in the classifier space here is that I don't want to have to bias my path by putting in my concept of what I think the configurations should look like as I go from one phase to the other. I want the machine learning to tell me that. All right, so I'm just going to give it environments, and it's going to tell me what it thinks those environments should be classified as. Now I can use this as a collective variable set to drive my enhanced sampling along with, for example, the cell parameters. And when you do that, you can see that you can generate very easily the transition, the motion of the interface between the A15 and the BCC phases. Okay. And not only can you drive one phase into the other, but you can grow the other phase back in. So you're getting statistics on the transition process. Now, if you do this at constant volume, you get a free energy profile that looks like this. And you can see very clearly a barrier for the transition of each layer. That barrier is about 0.5 EV. And although I don't have an experimental number for a system this small, I do have a kinetic Monte Carlo study that tells me that, it's about 0.5 EV to change each layer. So that tells you, sort of what the kinetics are. And of course, if you run this at constant pressure, then you see it's very much downhill from the A15 to the BCC. But each of these little bumps in here still is about 0.5 EV. All right, so about 50 kilojoules per mole. So we see that it's a metastable phase, but the barrier is high enough that you'd expect this phase to stick around for a while, this A15 phase to stick around for a while before you convert to the other. All right, how much time do I have left? Am I probably running close to the end, right?
Yeah, actually, you have already overshot by 1 minute.
Okay, so I'm going to finish up very quickly. I'm going to show you what we're doing for molecular crystals, and then I'll go into questions. So with molecular crystals, not only do you have the packing problem, but you have the orientation problem. All right. So what we're doing is we're creating an additional set of symmetry functions by taking a point vector representation, let's say in a molecule like urea, like this, where you have 2 points in the molecule, and you create a vector between them, and then you take the orientation, the angle between neighbors, and you can create a new set of symmetry functions for orientations. They're modeled on the ones that we use for packing, the G2 and the G3, but these will become additional descriptors for my my orientations. All right. And then when we have internal degrees of freedom, we'll take that into account as well as part of our enhanced sampling. Okay, so let me skip over this part and let me just, I know I need to come to the end. So I'll just acknowledge the people who have worked on this, especially Dr. Rogel, who's worked with me on the path collected variable work, and former students of mine who've worked on the various aspects of the crystal structure prediction. And of course, the funding agencies, especially the National Science Foundation and our Materials Research Science and Engineering Center, where a lot of this work got started. And so apologize for going over a little bit, but thank you for your attention, and I'll be happy to take any questions you have.
Thank you, Mark. Thank you for a very interesting talk. So I think we have time for a couple of questions. Yeah, Andrew. I saw Andrew's hands raised. So Andrew, please go ahead.
Actually, I think he's just
clapping.
Yeah, he was clapping. He wasn't actually raising his hand.
Yeah, terrific talk, Mark. Really enjoyed it. Thanks so much.
Okay. Yeah. So so anybody, if you have,
yeah, I think
so
yeah, okay, there is a question.
Jagannath.
Hi, Mark.
You
This is Abhijit.
Okay.
Oh, hi.
Abhijit.
Very
Okay,
nice
yeah.
talk.
Yeah,
Yeah,
hi.
can you hear me?
Yes, I do.
Okay, great. So I have a question regarding the simulation of the interface you showed. The interface was
Yes.
moving around. And so I just wanted to understand what the free energy means there, because in the actual dynamics of the interface, you're going to have certain types of diffusion mechanisms participating, which causes the phase transformation. And here, there are collective variables. So is there a connection between the real dynamics and this kind of dynamics?
Well, okay. No, I mean, this dynamics, what we're doing is not meant to be any kind of real dynamics, right? What it is intended to do, though, is to get a free energy profile, let's say constant volume and constant pressure. So you can see the difference between the free energy profiles, all right? So this gives you the profile along the S, variable in this case. So what the simulation you're looking at is not meant to be dynamical, but what we think that we're able to get right in this, very detailed and sort of complicated looking free energy, either here or here, is a set of minima and barriers. All right, barriers. The meaning of the barrier here is the work that you need, or the energy, the free energy that's required to transform a layer in your crystal from one phase to the other. And if that barrier is right, then you can use that to estimate the kinetics of any one of these transitions. All right, and it'll give you a sense of the time scale that over which this interface marches through your system. So that gives you an idea of how long it would take to convert, from one phase to the other locally.
Sure. Okay, thanks.
Okay, Sramoni?
Yeah, hi. My question is, much of your analysis depends on the information that you have a priori, the number of phases that or number of stable states that you are going to find. So my question is, what if you have missed something important? So will there be any signature in your calculations?
Well,
that you're missing something.
It's going, yes. So you could. It depends on how important that missing phase might be in any one of these transition pathways, right? Because if I missed something and I don't know that I need to feed that information into, let's say, a training set, then obviously it won't be there when I create this path. Now, if it's a sort of irrelevant phase, then it won't matter. But this, I think, what you're getting at is the importance of being able to explore enough that you've identified all the important phases, and that remains a big challenge. I'm not going to say that we have that solved. That's a structure exploration and structure prediction problem, and that remains difficult. Well, whether or not it's going to influence the pathway between any two phases, is going to depend on, let's say, where on the landscape that might be. Is it close that you have to pass through it, or is it far away that it simply doesn't matter? And you don't know that a priori until you've identified it.
Okay, thank you.
Okay, Mark, we have one more question here and then a couple of questions in the chat box. We'll go through very quickly. Anmol?
Yes, sir.
Yeah.
My question is kind of related to the previous two questions, but I was wondering if this methodology where you sweep around the whole potential surface, can this be applied to biomolecular systems, or because the CVs may not make sense, or the sampling may not make much sense in case of biomolecular systems, or machine learning can actually boil down or reduce the number of CVs which are actually important for a biomolecular phenomena to be seen, is my question.
Good question. So the CVs that we're using are, they're not designed for biomolecules. Obviously, we designed them for crystal systems, but the sampling methodology is general. And as I said, kind of in the beginning, we are working on doing this for biomolecules as well. I just didn't have time to tell you that story. But the idea would be that you can explore structures in a very high dimensional free energy landscape, on a high dimensional free energy landscape. And then let's say you pick two basins that you're interested in. And now we haven't tried, the idea of a machine learning based path collective variable there. So I don't know how well that would work, but what we're trying instead is to model the committer using machine learning. So the committer between two basins is being set up as a machine learning model. And well, you know, as I said, maybe at the next rare meeting, I'll have more to say about that. But the initial exploration is done using the same basic methodology, but with different collective variables. And I think you'll probably hear a bit about that in Nishant Nair's talk.
Thank you.
Okay, Mark, there are two questions in the chat box. We'll go through them very quickly. The first one is sort of a general question. The question is, I wanted to know about the computational time and complexity of running such an experiment. Probably he meant computer experiment, right? I believe. So
Right.
yeah.
Well, I mean, it's so system dependent, right? So in this case, you know, the length of our simulation was, I think, on the order of 10 nanoseconds or so, right? To get this interface migration. Generating the training data is not much at all. We do very short runs at these different temperatures, all right? So that's kind of negligible. Let's see, I think I have somewhere on here the range of temperatures that we use. And the training part is not, where was it? The training part is not that long. So we did, you know, 1, 2, 3, 4, 5, 6 temperatures, 6 or 7 temperatures. And we only generate, you know, 170,000 or so atomic environments. So these are relatively short runs on the order of tens of picoseconds, maybe, because MD for crystals is boring, nothing happens. So you just have to generate these environments with different amounts of thermal agitation. Training, not that difficult. That's actually relatively short. So the longest part of this is running this part of it, right? Getting enough data from your simulation to generate this kind of complex free energy landscape. And this is going to depend very much on the size of your system and the computing resources you have. So I can't really give a general answer to that question, but maybe I've given you an idea of what the breakdown is in terms of the different parts of the simulation.
Yeah. Okay, thank you, Mark. Mark, you could look at the remaining questions in the chat box, and maybe you could also give your replies, okay, in the chat box. I think because we don't have any more time left for this talk. So with this, let us thank Mark for an excellent talk, and now we'll move to the next talk. The next talk will be given by Ron Elber from University of Texas, Austin. Ron is going to talk on modeling membrane permeation. Okay, so Ron. Yeah, fine.
Yeah, let me each another second. Okay. Everybody see that?
Yeah. We could see your slide.
Thank you. So what I'm going to try to describe today is the research that you're doing in the last couple of years, and this is modeling membrane permeations. I will focus on one type of molecule, which is peptide. And in the cartoon here, what we see is that membranes are having a very complex structure with a lot of things, biological membrane, with a lot of things embedded in it, like channels, signal protein, and so on and so forth. So there are a lot of transfer that is done by the membranes in a controlled way by passing, for example, through a channel, but there's also what we call passive permeation, in which molecule of different size on a different complexity, just passing directly through the phospholipid and from one side to another for various purposes. Viruses, in some cases, they are indeed passing directly through the biological membrane, and that example is, for example, is the HIV virus. I will going to focus on one particular peptide, which is just sketched in here, and we'll talk why this peptide is so interesting. I want to emphasize that the fact that peptides are so efficient, that there are a class of peptides that are so efficient by passing through membrane, and doing something in the cell is actually quite surprising. The cell has a lot of machinery to degrade peptide very, very quickly, and the lifetime of particular peptide when you inject them into a living system is less than 20 minutes. So somehow they have to establish a lot of things doing this type very, very quickly. And this is short peptide and of orders of 30 amino acid. That is, it doesn't have a particular structure in solution. So it sounds like nothing interesting is likely to happen, but somehow it does doing a lot of things. So in fact, there are a lot of peptides that are called CPP in short, or self-penetrating peptide, that in many cases they can be agents of cells death. So somehow they can cause a different type of cells to die in very different mechanism. All of them are roughly of 30 amino acid long, so they are relatively short. Some of these peptides are antimicrobial, so they are killing all kinds of bacteria by the peptide is doing something to either to the plasma membrane or inside the cell. There are some peptides that are anti-cancer, and therefore they are very interesting from medical point of view, and are called ACP. Some peptides are both. So some peptides are both antibacterial, antimicrobial, and anti-cancers, and are of particular interest. The way that people find them or try to extract them from natures is they're looking for protein that serve translocation machinery. There are many proteins that by design, they need to permeate, to pass through particular membrane. And the first peptide that was discovered of this type is TAT, which is part of the HIV virus, and essentially is the leading peptide that allows the virus to penetrate into the cell. It is highly charged, and it's all arginine, and it took a while to figure out what the hell is going on in this particular charged peptide, given that the membrane is really made of hydrophobic environment, at least at the center. So most of the peptide, again, 1,700 of them that are known today, are derived from translocating proteins. And by given a particular CPP, we can use it also to carry certain cargo to the cell, and that is one of the ideas in which people are using CPP to try to cure cancer by peptide that aim at cancer. They're getting into the cell and then delivering something that will damage or kill the cancer cells as well. The deficiency of using CPP, and there isn't even a single CPP that is approved by the FDA as drug, is that they are, in many cases, they're non-specific. They're not really going into particular type of cell that we are interested in. And something that we already mentioned, which is the rapid clearance time. It takes only less than an hour in order to be washed out, so they have to act very quickly, or we have to protect them in some way using different mechanisms in order to make sure that they will reach their target. Sometimes you put them in another vesicle, like and target the vesicle into cancer cell and so on, but this is a whole new field out there that are trying to make them live longer and be more specific. The peptide that I'm going to discuss, that I'm going to describe some calculation on, is called NAF1-4467, and it is a self-penetrating peptide that is derived with a very different idea in mind. Rather than taking a translocation machine and chopping it off, it is a transmembrane protein. It's a piece of a transmembrane protein. I have the model of this NAF1 protein that is typically found in the mitochondria. This is a model. The crystal structure is not known. But what Rachel Nechushtai, she is the experimentalist that worked on this, she chopped off a piece of this protein, a part that is transmembrane and it's parts that is also well solvated, and use this peptide in order to do different type of experiment. And she showed, among other things, that this peptide selectively kills cancer cells. It does very little damage to normal cell, but real cancer cells, they are dying very quickly. And I'm going to show you some of a movie of a death of a cancer cell or a few cancer cells, in which we are taking a picture that were imaging that were prepared by Ron Mittler Lab in University of Missouri that collaborate with us. And essentially, you throw peptide on the cancer cell that you see in here, and the peptide, they carry fluorescent green probe. And if you watch it, you see the green color sort of growing at the membrane of the cancer cell. So here we go. The movie is on a speed dial. In the actual process, it takes a few hours, but you see that the green kind of color is growing more significantly at the plasma membrane of the cancer cell. That process takes hours. It's quite surprising that it's going to the plasma membrane cell, given that the peptide is charged 5 times, so it's 5+ charge. And after a while, you see all these bursts, essentially the cell explode and then they die. So all these things takes hours. And the questions that, of course, we are interested to know is actually what bring those particular peptides into the plasma membrane and make them stay there for a while, and how they initiate eventually the death. So that's the task that we want to address with using atomically digital simulation. Oops, somehow, oh, okay, sorry. So the questions that I would like to ask and partially address, okay, we have a peptide. What is the relevance of peptide sequence and secondary structure to this? As I mentioned, there's a huge number of CPP. Some of them are targeting different membranes. Some of them are targeting different cells. What are the physical forces that essentially bringing this peptide into the membrane? And can we propose some at least qualitative sequential mechanism that we can build on when we are attempting to use different peptide, design the peptide for different membrane, and so on and so forth. NAF1, for example, without any further design of what I'm just described, is passing through the plasma membrane of cancer cell without damaging the plasma membrane, and is going to mitochondria. And once it is going to the mitochondria, it is kill the mitochondria, and then the rest of the cell die in the same picture that we have seen. So the peptide is positively charged. So how 5+, how is the peptide trapped in hydrophobic membrane for such a long time, as we have seen in the movie? What essentially is the free energy barrier? Because, you know, hours is a long time, and you can argue that this is a rare event for this small peptide to go to the other side. And if we really would like to know what does it do in order to kill the cancer cell, but for that I don't have an answer, so we leave this as an open question here. We want to simulate this peptide membrane system using a atomistic model to try to get the best insight that we possibly can. And there's a number of challenges. The obvious one, that this is really a very long time process that extends on many scales, starting from nanosecond, in which the peptide is attached to the membrane, and attached to the membrane surface. That's the typical time it takes, until hours and even days, in which the entire process has been completed, that the membrane went into the membrane and then leave from the excited system. The system is large. I mean, and people have done larger systems these days, so this is perhaps not the most important factor, but nevertheless, you can go into hundreds of thousands of atoms, and you are really trying to model well the membrane and the aqueous solutions and so on and so forth. It's a very complex environment. When you pass inside to the membrane, this diversity of different environments is definitely far from homogeneous. It's going to change as a function of a membrane depth, as the peptide is going in more and more inside, which is partially heterogeneous. There's a different dielectric, there's different fluidity and viscosity. And on top of all these problems, if you like, or all these challenges, the peptide is that of length of 30 amino acid, which is unstructured in water, is very flexible. And somehow we need to make sure that we are sampling at least the important conformation of the peptide when we are doing this type of calculation. What we are using a method that we developed, I mean, almost 20 years ago, and we keep developing it, but it's the method of milestoning, and it is based on certain algorithmic steps that I'm going to outline in here. It is sort of well documented, and it can be made exact, and you can also do some hierarchies of approximation, which is also useful. So the first thing that we need to do, which is a step that we can also use input from a lot of smart people around, like Mark, that can help us in order to find what are the best cost variables. The cost variable that we choose, they are really based primarily on chemical intuition. They are not rigorously being derived, but that chemical intuition, in many cases, if you have good intuition, it works quite well, as I'll try to illustrate. And we have internal check within the calculation to make sure that the collective variable that we have done are really leading, that we have used are really leading to converged result. So once we have collective variable, and here this is an illustrations of two collective variables, call them Q1 and Q2, or what we call also coarse variable. We need some rough sampling in the coarse space. It doesn't have, we don't do, of course, comprehensive sampling, especially that we are working in some cases in 3 dimension, and that's not very practical, but we can still sample roughly this conformation space. And here there are conformations, or what we call anchor. These are the blue circle in this conformation stage that we sampled previously, and they serve for us as centers of Voronoi cell. It needs to be very coarse. It doesn't really have to be in with high resolution. Typically, the distances between those anchor or those centers of Voronoi cell is about an angstrom, and or less, or a little bit less. But what we do, given those anchor in core space, we first what we do, we initiate trajectory starting from the anchor, or starting from the blue circle in here, and this is the red line that we've seen here. This is a relatively short trajectory, they're of picosecond length, in which we are running them starting from the center until they hit a milestone. And milestone is an interface between Voronoi cell, like the thin blue line in here, or the mesh that we see in here. Once the trajectory terminates at a particular milestone or at a particular interface in here, we stop and we mark this milestone as active. This is milestone that we sort of sample it when we start from the Voronoi cell. And we started from the anchor at the centers of the Voronoi cell. We do it for all the sample configuration. And once we are done, we take all the sets of active milestone, and then we sample at the active milestone with a constrained sampling procedure. So we run a molecular dynamic trajectory here, which is confined into the line in here or to the milestone in here, and we are getting a numbers of conformation at this particular point. Once we are doing it for all the milestones that are active, all the milestones that we are identified, then we run unbiased trajectory from each of the milestones, like the green line in here. We're running until they hit for the first time another interface or another milestone, and then they are terminated. These trajectories are also typically short. They rarely exceed a nanosecond. So we have many, it can go to 100,000 or up to 1 million short trajectory, and which you can done in massively parallel way, but there are quite a few of them. What we collect from this calculation are essentially this short green trajectory. We collect what is the probability that you start with a particular milestone and you end at another interface. Given that you start from here, what is the probability that you end up here? And we also collect the time which take the trajectory to reach another milestone. These two entities are all we need in order to calculate some interesting thermodynamic variable. We calculate it so-called Kij. This is the probability that a trajectory that starts at milestone I will hit milestone J for the first time. And in the language of trajectories, essentially the numbers of trajectories starting from I and ending at J, dividing by the total numbers of trajectories that starting at I. This is our estimate of this Kij. We also estimate the so-called TI, which is the average lifetime of a trajectory initiated milestone. We have multiple trajectories getting out from a particular milestone. Some of them live long, some of them die very quickly because they terminate on another milestone in another position. We average over all this time, and we are getting the lifetime of a milestone, regardless of what are the milestones that are finally terminated in. Giving these two functions, Kij and Ti, we can get essentially a lot of information about the thermodynamic and the kinetics of this system. For example, the one thing that we can compute is the stationary flux that is passing through the milestone. It is the eigenvectors of this matrix K, which is called Q here, with an eigenvalue of 1. So once we got this Kij, we can determine the stationary flux that passes through the milestone, which is Q. Once we know Q, we can get the probability that the last milestone that we passed is a particular milestone. And this is a scalar product of Q, the fluxes, multiplied by the time. So essentially, the way to think about this, you have trajectory that are coming into the milestone, how long they're going to stay there, essentially determine the probability that they are going to be still associated with this particular milestone. So this is essentially the probability, if you like, of being at a particular milestone. And of course, the log of it, like Mark also said that we are going to see it many times, is giving us the free energy that we see in here. We can also calculate the mean first passage time, which is the probability, Q times T, divided by the flux into the final milestone, into the product state. Another thing that we can compute, which is exact within the framework of milestoning, is the commuter function, which is given by this formula in here. It's I minus K, the same K that I wrote in here. And this is a vector EF, which is 0 everywhere except 1 at the state of product. So these three functions are the ones that I'm going to discuss further: the free energy, the mean first passage time, and the commuter. So the first thing that I would like to comment about is how we extract the anchor, or how we get the pictures of the Voronoi cell. This is a non-trivial process, as I mentioned, because of the complexity of the system. One naive idea that we had, we said, okay, this peptide has 5+ charges. It must really hate being in a heterophobic environment. So we put the peptide at the centers of the membrane, constrain it there, and run equilibration time, given that it is constrained in the membrane, and then we let it go. Then we watch many trajectory, which we hope will rapidly go into one side and to the other, and then we can try to look at it, and by visually inspecting it and doing further analysis, trying to understand what are good course variable to describe the motions of this particular peptide from one side of the membrane to another. This is just a sample of one of the trajectory that we play around, and I'm playing it in reverse. So it's coming from the water until it hit the middle position in which we started with. It turns out to be very hard. Actually, the peptide likes to be at the centers of the membrane. And at the end, we have no other choice but really biasing the simulation with still molecular dynamics to get sensible conformation that we can build on, and we can build the anchor for calculations of milestoning. So as long as we have reasonable cost variable, which we extract with the help of SMD, we can do the milestoning without any further bias. So the free course variable, essentially they are here, that we settle on, are essentially three distances to the membrane center. This is the distance of so-called of the leading amino acid, phenylalanine number 1, to the center, and arginine 14, which is at the end of hydrophobic helix that we see in here. The peptide does not have structure in aqueous solution, but once it is going to the membrane, at least half of it is adopt a well-defined helical structure that we see also in here. And K24 is at the other end, at the C-terminal. So we have three distances, and they are sufficient for the calculation we have done. We tried many other course variable, like the trivial one, the centers of mass of the peptide, and things like this, but these three sort of works for us the best. They're probably not unique, but they're working for us, at least for the calculation that I'm going to present. This is the free energy landscape, and it is color-coded, and this is shown in 3 dimensions. I'm going to sort of rotate the free energy landscape in 3 dimensions a little bit so we can appreciate a little bit more the structures of it. Blue means minimum. So the free energy landscape is such that there is a minimum at the centers of the membrane, and red means high barrier, and the barrier for the entrance of the peptide are essentially at the edges of the phospholipid heads, or at the edges of the membrane, in order to get in. So once it is inside the membrane, it is pretty happy and doesn't require any more help. And this is sort of consistent also with the movie that we have seen experimentally, in which the peptide was essentially practically was trapped for hours in the membrane before it went on into the cell to initiate cell death. Here is another kind of a cross-sections of this three-dimensional energy landscape. This is essentially the same picture that we have seen before, but with cross-section is sometimes easier to see. I also draw on the same plot the so-called max flux pathway. We now have a network, because all this Voronoi cell with the milestone in between can be described as a network with edges that are connecting between the cell or between the milestone. On the network, we can ask what is the pathways of this particular network that carries the maximum numbers of trajectory, and from this extract a one-dimensional picture that can help us in interpreting the result and understand what is going on in this particular system. So this kind of a not so smooth line, that red that we see in here, is essentially the max flux pathway. We see that it's not really monotonic in any one of the course variable, so it's not that you can forget one and get on with a reasonable calculation. There are some numbers here that I see, like 1, 2, 3, and 4. These are images that I could use to try to qualitatively explain the mechanism that I'll show in the next slide. So essentially, we are getting the free energy profile. We are getting one suggestion for the mechanism that we can explore further. And this is shown in the sign kind of a static movie in here, or with the sequence of images with the number correspond to the same number that I've shown before on the free energy landscape. So what we have in here, this is like a step 1, is the peptide lying flat on the phospholipid of the membrane. The peptide is hydrophobic, and the strongest interaction is with this arginine 14 here, which is positively charged, and the negatively charged phospholipid. And that's essentially the transition between 1 to 2 is the significant barrier that we see. And then after the significant barrier is overcome, essentially when the hydrophobic helix permeate in, then it's getting in even deeper in state 3, and until the charge group that we see in here of arginine 14 is sliding inside into the membrane. At the interface of the aqueous solutions and the membrane, now we have the end or the C terminal, which is K24 or lysine 24. And then the peptide need to do some kind of an interesting maneuver, because it need to turn around and change its direction such that it can go in a symmetric way to the other side. So there's a whole kind of a significant change in conformation that we see in here, in which the peptide is essentially completely buried with 5 pluses inside the membrane. At the same time, it distorts significantly the membrane. The yellow ball that you see here are phospholipid that is attracted inside into the phospholipid, but eventually it reverses its direction from going down. Now it's going up, and the other part of the chain is getting out. This is a cartoon model of the same thing, just to show it perhaps more clearly. And the steps are flat on the surface, hydrophobic helix coming in, then it is dragging with it one charge. The membrane simultaneously at this step is being significantly distorted to sort of compensate, if you like, to the charge in here. There are many waters, up to 1,000 water molecules that are coming in into membrane at this particular positions, and also phospholipid are getting closer. Then the helix turns around and eventually reverses its directions and moving out from the other side. Another function that's sort of telling us roughly the same story, but in a different picture, is the commuter function. We can calculate the commuter function, and the commuter function is the probability that we are starting from a particular point that we will make it first to the product versus the reactant at every particular point on this 3-dimensional cross-section of this 3-dimensional shape. So the blue here means 1. So if I start from the product, this is the final escape state of the particular peptide, the probability that obviously I make it to the product is 1. If I'm starting from the reactant very, very far, the probability is close to 0. At least it's very, very low, and this is essentially is indicated on the color bar in here. But the remarkable things about this plot that I was sort of surprised when I saw it first is that extremely broad, if you like, transition state that we have in here. The transition state is around 0.5, which is the color of a light green that you see here at the center. Essentially, more than 80% of the energy landscape is a transition state. It's a completely flat energy surface, which is, again, is consistent with the pictures of the peptide turning around. It turns around rather freely. Also, the free energy has a minimum there, and it's relatively free to move. So extremely broad transition state and barrier at the beginning and at the end, that is a kind of the picture that we have for the peptide permeation. The extremely broad transition state or extremely broad intermediate state, again, consistent with experiment of trapping the peptide for hours in the cancer membrane. Oops, what happened now? Oh, okay. So we can look at also the mean first passage time, which is another thing that we can try to compute within the milestone theory. And the things that I want you to appreciate in here is this is a log scale of the mean first passage time. And essentially, there's a very sharp increase in the time that is required to move from the last piece of the reaction, this is moving along the one line max flux pathway. We calculated the MFPT at every particular point. If you move from the edge, which is around 80, to outside to the aqueous solution, it can take you 6 orders of magnitude in time, compared to the time in which the peptide is just moving around inside the membrane. When it is trapped inside the membrane, the time scale is only of orders of 1,000. It is doing it very rapidly, many conformations that it can explore, and we can capture those kind of minimum and flexibility of the peptide within the membrane by looking at the max flux pathway and the mean first passage time that we have in here. We also have some experimental evidence for this, and this is an experiment that was done by Drexel Chad and Lorraine Webb at the UT Chemistry lab. And what they took essentially the NAF1 and they tried to attach it into a vesicle, which is a LUV vesicle. They are made for DOPC. They are very, very stable. It's very hard to permeate in, but at least they can see clearly the first step of the permeation. So first, they took this particular peptide and they put it into 2 different solutions, one hydrophobic solution, which is hexane, and then you see sort of a blue shift that the wavelength becomes shorter. And if they are putting it compared to aqueous solution or a buffer solution, which is what the HEP has seen here, then they repeat the same experiment in the presence of the vesicle. So after a while, first what they're seeing a shift into red, and this is the red line in here. The orange line that we see here is essentially the same as in aqueous solution and HEP solution. The shift to the red essentially can be interpreted as the peptides situated at the surface of the membrane have strong interaction with the charged phospholipid group and therefore make the spectra a push into the red. The probe that they put on the NAF1, I did not mention that, is attached to the N-terminal in here. It's a Danzil group. So here it sort of fills the phospholipid head group or the charged phosphate group, and therefore it is shifting into the red. But once the N-terminal is getting into the membrane in step 2, there's a significant build-up of a shift into the blue because we are now in hydrophobic environment and there's no longer interaction with other charge group. The peptide or the charge group are on themselves. So that's what I wanted to tell. That's the short story that I wanted to tell. So NAF 4467, 44 and 67 are the sequence positions at the original protein. Is a novel CPP. The first time we derive it from a transmembrane helix that essentially is embedded in the mitochondria and the ER membranes. And it is a peptide that is sort of consists of essentially 2 domains, one hydrophobic terminal segment, a helix segment, and a C-terminal segment, which is carries a total of 5 charges. This is a mistake in here. So the proposed mechanism essentially tells us that these significant barriers at the boundaries of a phospholipid head and aqueous solutions and a broad minimum at the membrane system. And it took some effort, but this calculation took us like 2 years or maybe even a little bit longer. But I think that within the milestone calculation, we were able to do that using a script, Python script that we are making available. And we are used as an MD machine, we are using the GOMAX program. Acknowledgement, and then I'm done. Thanks first for Alfredo for doing all the calculation. Rachel is the one that actually discovered this particular peptide and did many biological experiments with it. She actually can cure now mice, cancer in mice these days, and we hopefully will be able to progress even further. Ron Mittler did a lot of biology experiment, and as the movie that I have shown you, and Lorraine Webb making more of a chemical physics type of experiment that can test better the calculation and provide us with important feedback. And thanks for the funding. And thank you.
Thank you, Ron, for finishing in exactly 30 minutes. Thank you so much. So there are a few questions on the chat box. Maybe we'll take a few of them. The first one is by Anand Srivastav, and I see Anand's hands are also raised. So Anand, would you like to ask the question by yourself?
Yeah, hi, thanks. Can you hear me?
Yeah.
Yeah.
So very nice talk. Actually, I have 2 questions. None of them related to rare events, I'm sorry. So the first one is what I typed in. How do you see the, the pathway that you have suggested of kind of snorkeling and symmetrically moving on the other side would change if you have multiple peptides subjected to the bilayer? Do you see any changes happening? I think you kind of answered this when you were showing some of the experimental evidence. So that is the first question. I would like your thoughts on that. And the second question is related to the imaging, the video that you're showing of the cells with the green color showing the peptides. I noticed that these peptides were not localizing in highly tubular regions of the membrane. Do they only penetrate on a more flatter surface, or is there something known about their getting into the membrane mechanism? Like, how do they really do they need the tubular part? The two ends of the cells were not getting affected, and also the cell size kept shrinking. I don't know if it was right or not before it burst. So can you please shed some light on these aspects if possible?
So yeah, I mean, that's all very good question. And unfortunately, I don't have that many answers on the biology part. This is something that we still study. It depends on the type of the cancer. You can have different type of cancer cell that they respond differently to this. The peptide does not seem to go into particular positions in the membrane. It seems to be widespread. In fact, it is passing the plasma membrane without affecting the plasma membrane. The plasma membrane seems intact, just going directly through the phospholipid. What it does kill, and for that we do not have such a nice imaging yet, is the mitochondrial membrane. So it is going to the mitochondrial membrane and destroy it. We have guesses, but they are really guesses, and I prefer not to guess it more at the moment at this particular point. Now, the mechanism that the evidence that we have for this is for interaction is this type of experiment in here. We do not have more evidence experimentally, but we are working on it. So that's the part of the mechanism that we think quite strongly about that the peptide is getting in the membrane first. That we see also in the biological part, and the chemical physical experiments suggest that this is the first step. The rest of the step, I don't have a proof.
Okay, thanks a lot.
Sure.
Okay, so we'll go to the next one. That's from Jagannath. I'll read the question, which is there in the chat box. How does the initial SMD that you had carried out would have biased the generation of pathway for milestoning?
So it can, of course, bias. I mean, this is a very complex system with too many degrees of freedom to start with. But what we do, we have all those configuration and anchor, and we run short trajectory from them. Some of this short trajectory, they're going and finding something new that were not discovered initially. And we add them in and we repeat the calculation. So essentially, we have like a small network that allow to grow as and expand. And at some point, when we do not discover anything new, then we stop. We say that we are converged. So, but it's definitely possible that, 5 angstrom away from this pathway, there's another mechanism that we never sample. So that's the question that I cannot address. What I can address is that the network, at least that we generated, seems to be converged, is consistent within itself.
Okay, thank you. I think we have 1 more minute, so we can take one more quick question. That's from Nishant. How many course coordinates can be considered in practice? Have you tried generating biased trajectories from milestones? So, okay, so I think that the questions of how many coordinate is important, and in principle it can be large, but we are not going to do exhaustive sampling of that space. It must be some constraint on that space such that you can really sample only a narrow band, if you like, of the full conformation space. In that case, even in the free, it can be quite expensive, but the fact that the space was relatively narrow make it really possible for us. I would say that I would not even try something more than 5. So that's just beyond what we can do. Okay, fine. Okay, thank you, Ron. There are a couple of other questions. If you could please have a look at the chat box and and reply to those questions. That will be wonderful.
Okay, I will
With
do that.
this, I think, please join me in thanking Professor Ron Elber for his wonderful talk. Thank you so much. Thank you.
Thank you.
As per the schedule, we are supposed to have a tea break now, but looks like we have already consumed that tea break. So if it is okay with everybody, we could just continue with the next talk, and please feel free to have your own cup of tea and join back the meeting, okay, whenever you can. So with this, Nishant, so should I just continue?
Yes, yeah, please.
Okay, fine. So then the next talk will be given by Nishant Nair from IIT Kanpur. He is going to talk on efficient exploration of high-dimensional free energy surfaces. Nishant?
Yeah, thank you so much. I have to say that being person who also arranges for the conference, it's pretty difficult to give a talk actually, because I am not sure all the slides have been put properly. So excuse me for that. This is a work that we have been doing for the last 3-4 years, and I'm really happy that in this platform I can give my talk. And thank you, Amalendu. And let me start. So the idea of this talk is it's a technical talk where I will be talking about some methods that we are using to explore high-dimensional free energy landscape. Of course, the thing that I'm going to talk about is where we are going to talk about free energy in collective variable space. So I'm assuming that we have somehow no collective variables that are good for the problem of our interest. So for example, drug binding, unbinding, I'll show maybe we may need something like 25 collective variables to kind of sample all the conformations, and also maybe to also understand what is going on within this molecular system. We're not just talking about 2 collective variables like I've shown here. It's something like very big. Okay, like it could be 8, it could be 10, it could be 15, it could be 20, something like that. Of course, all of you know about biased simulations and unbiased simulations. In unbiased simulations, especially if you're doing a molecular dynamics simulations without applying anything, any biases on that simulation, what you can do is to follow the collective variables as a function of time, get the probability distribution, and then of course get the free energies. In bias simulations, where you will be able to see these transitions between different states very rapidly. So for example, here these transitions could be milliseconds, but in a bias simulations that could be simply picoseconds. We also can get a distribution, but that distribution is a biased distribution, and we need to worry about how to get the unbiased distribution from the biased distribution, and of course then get the free energy. So that's the usual approach, and there are various techniques in this field. So umbrella sampling is one of the old techniques which is used even now quite heavily. So in this approach, what we do is we of course put some restraining potentials on some collective variable space, and then for each of these windows, which is basically the restraint potentials, we'll do molecular dynamic simulations, then obtain the probability distributions for each of these umbrella windows, and then stitch them together to a full distribution. And you can use WARM, or there are similar approaches for getting these kinds of distributions. But you should, and of course, I'm missing one slide. I can see that. Just excuse me. Yeah. And there are other techniques which are quite popular today. Is metadynamics, where we put a biased, a bias as a function of time, like the bias which is shown here. These are Gaussians added on the trajectory of collective variable space, and that adds up the bias, and it compensates the underlying landscape and let the system diffuse from one basin to the other. And at the end of the day, you can obtain the free energy estimate by using the bias potential itself. But the issues with these techniques, which usually is I mean, it's pretty popular today, right? Both umbrella sampling and metadynamics is that we are restricted to very few collective variables. In practice, usually 1 or 2 collective variables is what people use. And but we know that if there are hidden coordinates, things get poorly sampled, and that leads to very poor convergence. So this is a very typical issue that all of us face in umbrella sampling. You can see that the distributions are converging very, very slowly. Okay. And if you just look at one part of such a free energy landscape, so let's say that the system is just exploring a particular part of the collective variable. Let's look at a realistic example here. This drug is at a given distance d from the active site, and you can see the kind of conformations it's sampling, right? So it's very easy that the system gets stuck in any of these conformations, and you can easily miss very important conformations when you're doing the free energy calculations. So we need possibly more than one collective variable, so more than 2 collective variables, because there are a lot of coordinates to get accelerated so that we can sample all these conformations rapidly, so that we can converge the free energy estimates also rapidly. Okay. And in this direction, one of the most important techniques in this area is the temperature accelerated molecular dynamics, or DAFED approach, which is very cool approach actually, where what you do is you extend the degrees of freedom here by some auxiliary variables. So these S are auxiliary variables, and these auxiliary variables are actually kind of mimicking the collective variables. Okay. And the way that it mimics the collective variables is by using these restraining potentials. So these restraining potential kind of keep these auxiliary space close to the real coordinate. Okay. And this was originally proposed by Professor Mark Tuckerman, and also then Van Eyden has also proposed in 2008. So some of those references I will be showing a little later. So the idea here is, Mark has already discussed about this. So the auxiliary variables are kept at very high temperature, but the real degrees of freedom are kept at the physical temperature. And what is critical is to make sure that there is an adiabatic separation between these two space, so the real collective variables and the auxiliary space. And of course, by temperature, you will be able to sweep across the collective variable space very rapidly, and you will be able to converge the probability distributions also quite rapidly. Finally, you can get this free energy estimate, and I have also posted a link on the chat box where you can see Mark's handwritten notes of derivation, and also you can see various papers as well as his textbooks. I'm not going to give all the references, but you can look up the link that I have posted in the chat box earlier, where you will see the full details about the technique. The advantage of this is that it's not a serial technique like Mark was saying. So it's kind of a parallel technique. So because you're just exhaustively sampling large number of collective variables parallelly, right? And so therefore you can include large number of collective variables, and that is actually quite good for the problems of that I have shown, like where the drug is getting stuck in some part of the protein, right? I mean, you need some collective variables to exhaustively sample, like the detachment from that part, and then go somewhere else. Then you need collective variables to detach the drug from the other part of the protein, and so on. So you may need to really also revise the collective variables as you start the simulation, right? So. But there are also other problems. The problem is something we are very familiar with. When you want to go from a point A to point B, there are a lot of obstructions, right? I mean, the energy that you have in the morning to go from your home to the office will get wasted just because of the traffic block that you have to face. So the system, I mean, our interest is to go from A to B, but of course, the system would like to diffuse on this collective variable space because there is no barrier there, and I'm not really interested in going to those spaces. Okay, so of course you can put a wall potential and do the simulations, but it can become tricky for systems where you do not know where to put the wall potentials, right? And also wall potentials introduces some artifacts. So what we need is a highway to go from our office to our home to the office, where we can, the biases, for example, you're applying to the system is directed along a particular collective variable, for example. Okay, so that the system is really driven from a point A to point B without exploring the places that I don't want to explore. So a wish list of features that I want in my collective, in my hand sampling technique is something like this. So a quick sampling is needed. I need large number of collective variables. I need very quick convergence of free energy. I need controlled exploration in many problems, like, for example, diffusion through membrane, drug binding, unbinding, protein folding, and so on. I would like to use different collective variables as I start my simulation, because I would immediately realize that, oh, I need more collective variables because some system is getting stuck there. Right, so I need that features as well, without really diminishing the performance of the technique. Of course, I need a very quick reconstruction of the high dimensional landscape. So these are my wish list, and we are working towards that. And in this direction, we came up with this approach, inspired by Mark's DFAD approach, where what we do is that we choose collective variables, then we use auxiliary space connecting to these collective variables. And then we introduce an umbrella bias along one of the auxiliary space to drive the reaction from point A to point B. But there are different local coordinates that I would like to bias, because there are like bond breaking, sampling of conformations because of the torsions. So those are better enhanced sampled by metadynamics. Okay, and all of these and many more can be enhanced sampled using high temperature, like in DFAD or TAMD approach, where there is a thermal bath that couples to this auxiliary space, and that the high temperature enhance the diffusion of this auxiliary space in the high dimensional CV space. So this is what we call TAS, the temperature accelerator slice sampling. I call it slice sampling because it is actually sampling a slice of a high dimensional probability distribution, because you're restraining the system along one particular coordinate. Okay. So here I have shown that only one of the coordinate is biased by metadynamics, but it could be two, but it could be three as well. But as you know, metadynamics bias growth rate will diminish rapidly if you go, or exponentially if you go with the increasing dimensionality. So this is, so to say, a mix of umbrella sampling along one collective variable and metadynamics along a few collective coordinates, while temperature accelerated MT or DFAD approach along all the n collective variables that I've chosen, where n is quite large. So this could be achieved by this Lagrangian. So here you can see the auxiliary space, which has some kinetic energy, and this is the coupling of the auxiliary space with the real collective variable. And this is the bias to drag the system from A to B through an umbrella restraint potential. And then you have a choice of applying metadynamics along one coordinate or two coordinate. And I will show you a modification of this, where I can actually independently sample, or I can actually bias large number of one-dimensional collective variables using metadynamics. I'll come to that a little later. There are many parameters that makes it not a black box approach. So you can look at one of the earlier papers of Mark, where he discusses about how these parameters can be identified. And we are also working to come up with kind of making this approach a black box approach. I hope we'll achieve that soon. So we can discuss this a little bit later, but it's definitely, you have to put some effort to find these parameters, like the mass of the auxiliary space and coupling constant and so on. To reconstruct the free energy from this technique, because you have different kinds of biases applied on different collective variables, you can use Pratyush and Michele's reweighting scheme, where you have time-dependent reweighting scheme. Again, I'm not really going to discuss all the details about this, but what you can do is you just know, if you know the bias along the collective variables, you can you have a time-dependent reweighting factor that can be included or calculated, and based on that you can construct or you can use a time-dependent reweighting and get the distribution. Okay, so in our case, what we are talking about is the reweighting of each of the distributions. I mean, because we have umbrella bias potentials, so each umbrella potentials will have its own distributions. So we are talking about reweighting these individual distributions of each of these umbrella windows. Of course, then you can use weighted histogram analysis or other technique, which I will discuss very quickly, to construct the full dimensional probability distribution. From there, again, you can use this equation which Mark has already shown, how to get the distribution of the collective variables at high temperature to the low temperature. So you can easily get this simple expression to get the free energy at the physical temperature. Okay. So this, the advantage is that large number of collective variables can be treated like the TAMD or DFAD, but also that you have now, you can drive the system along one particular direction and locally enhance sample using metadynamics, okay, bias potentials. So this is just to show you very quickly the convergence behavior. This is just alanine dipeptide example. So it's not the best thing to show. Okay, this is where only one coordinate phi is biased using umbrella sampling, but the other coordinate, the psi, is by metadynamics, and all. I mean, these two collective variables are kept at very high temperature. This is just a model system just to show that, you know, the task estimate is converging very quickly. Okay, but metadynamics will take. You can see this. The red is the task data where you know, that's in the top panel. Okay, so 6 nanoseconds per umbrella window. So we have like 33 umbrella windows in this particular case. So, but this is metadynamics, and metadynamics is serial. Okay, the normal metadynamics is serial, and you can see that converges very slowly. Okay, and these umbrella windows usually we run parallel. So you know, in half an hour or less than half an hour for alanine dipeptide, you get the converged free energy surface. So let's go to something more exciting, right? I mean, because alanine dipeptide is nothing exciting. So let's look at alanine tripeptide in vacuo. So this is where we have used 4 collective variables, and phi1, phi2, psi1, psi2, 4 collective variables have been used. And you can see the convergence of free energy barriers. So these are free energy barrier convergence. These are the free energies of some of those you know, second order saddles on the free energy landscape, the projected free energy landscape, and you can see they are converging extremely quickly. Okay. And as I told you that I mean, we are not running like one window after the other, right? We are running all the windows in parallel. So in short span of time, you converge this very quickly. So there are examples of tutorials for doing tasks for alanine tripeptide. I will show you. I will give you the link in the chat box, so you can try by yourself. You will see that it's so rapid in convergence. And we have used, again, auxiliary space were kept at 3000 Kelvin. We use GGMT thermostat, and GGMT thermostat is critical for this calculation, because we found that otherwise the error can be substantial. So GGMT thermostat is applied on the auxiliary space and the physical degrees of freedom. And this is the usual replica exchange molecular dynamics simulation. And this is TAMD DFAD, just for your reference. This is after 15 nanoseconds. Of course, it's only one window, but we have 33 windows. Okay. So what is exciting here is this table. I don't know if it's, I hope it's clear. So this is the L square error that we have calculated. So L square is calculated with reference to a reference free energy. And this is the replica exchange molecular dynamics free energy, the surface that we got, that's a reference, and that's obtained after 1 microsecond. And you can see that you know, the task convergence is pretty quick, right? I mean, it's less than 1 kcal per mole I can achieve within 10 nanoseconds per window. And what is here is the efficiency of exploration. Okay, so the efficiency of exploration is calculated like this: the number of bins it visits in the 4D free energy surface, okay, divided by total number of bins. Okay, so you divide the 4D surface in the bins. So in our case, we divided it into 26 power 4 number of bins, and we counted how many bins have been visited as a function of time. Right? So you can see in 1 nanoseconds per window, you have like 47%, so almost half of the 4D surface has been spanned. Okay. And is so basically what we have making use of is the divide and conquer strategy, because we are dividing these high dimensional surfaces into small pieces and sample them. So that makes the sampling very rigorous in some of the regions where the system won't like to go. Okay, otherwise. And of course, the advantages of temperature acceleration and the metadynamics bias that we are applying. Okay. So this is quite encouraging because we are achieving quite rapid and very exhaustive sampling of the free energy landscape, and the method is quite accurate. So we have also come up with ways of avoiding warm, because weighted histogram analysis makes sure that the distributions are overlapping. So we have way to overcome this. This has been recently published. So the idea is that a high dimensional free energy surface can be written as the projection of the free energy along one coordinate and a sliced distribution. Okay. And the details I will skip because it's already in the paper, and this slice distribution and this projection can be computed separately, and that we don't really require any weighted histogram analysis, because these are directly coming out of the TAS umbrella window distributions. So the free energy along the bias coordinate can be directly obtained from unbiasing the umbrella bias, the force that are acting on the coordinate where the umbrella bias is acting. And the other distribution can be used by Prithush's reweighting scheme, and that's also straightforward, and we can actually reconstruct free energy landscape pretty quickly. Okay, and also this allows you to use less number of umbrella windows than that we had to use in the case of a weighted histogram analysis. For example, this is the case of alanine tripeptide. In the case with 20 umbrella windows or 40 umbrella windows, you can see that the barriers are nearly the same. A to B barrier or B to A barriers are coming out to be the same, and the L2 error is very, very small. Okay, I mean it's extremely small. So this is what nowadays our group uses. We don't use weighted histogram analysis anymore. We use the mean force approach to reconstruct the free energy landscapes. So we have applied these techniques to various cases like enzymatic reactions. We have published a couple of papers. We have looked at ligand dissociation. We have looked at reactions in zeolites, and these are, I will post these papers in the chat box so that if somebody is interested, they can look up. I'll very quickly show you one example where we looked at the drug binding unbinding problem. This is an antibiotic binding to the active site. So we have used different setups, and I will show you explain these setups to you. So in one setup, we have looked at the ligand to the active site distance as one of the collective variable. Then we have looked at the torsion of a relative orientation of the ligand. So we described that using a torsion. And when we did this calculation, when we do the normal metadynamics or using the TAS approach, you don't really get the free energies converge very quickly. Okay, in fact, you start getting minima on the places where you should not see any minima. Okay, and the reason why that happens is that the system is getting stuck in different parts of the like the picture that I have shown. Okay. So for example, you can look at this case where you can see that there are bulk water molecule coming in, staying there in the active site for a very long time. Okay, and the active site water is not really going out. Unless the active site water moves out, the drug cannot really diffuse through the channel. Okay, so you need to have some kind of collective variables to accelerate these things. So what we realize is that we can actually use all these collective variables that I've mentioned here: distance of ligand to the active site, torsions, which samples the orientation of the ligand. Then we also need active site ligand coordination collective variables, and some kind of hydrogen bonding interactions with all the residues that are in the channels. Okay, so you use these 4 collective variables, and then some additional collective variables that basically moves or enhance the sampling of the ligand on various part of the protein, right? Because as it comes out, it can get stuck in some part of the membrane, so some part of the protein, like here. Okay, I mean, it stays here for a very long time. It won't really diffuse on the surface of the protein, right? So with these collective variables, which is this kind of a distance of this inhibitor from various part of the protein, we are able to basically enhance the so to say the diffusion of the ligand around the channel. Okay, and that gives you converged free energies very quickly, and I will show you some more results in the next slide. And I mean, this is the free energy landscape and projected onto 2 dimensions, and we can also kind of track different pathways of binding and unbinding, because you have now full picture of how the drug is basically unbinding from the active site to the solvent. Okay, so if you look at if you do a typical umbrella sampling simulation, you see that this convergence is very, very slow. You do go for 50 nanoseconds, you are not very sure what's going on, right? Because you see that it keeps dipping and nothing is really converging. Okay, but you can see in task simulations, when you do task simulations, it converges very quickly. Okay, and not only that, you can look at the conformations, right? I mean, it's very exhaustive. It's not like in umbrella sampling, but it's extremely quick, and you can even 20 or 30 nanosecond is good enough for you to get a very good estimate of the free energies. And you can see that the water molecules are diffusing in and out very rapidly in task simulations, but in umbrella sampling, it really gets stuck in the active site for a very long time. So very rapidly, I mean, this is the Amalendu, how much time I have? Almost done.
No, you have 5 more minutes.
5 more minutes. Okay, right, yeah. So very quickly, we have a slightly different version of task where we can actually use several 1D biases, like in the case of parallel bias metadynamics approach by Jim Fander and Bonomi. So we have basically used the parallel bias scheme of Jim Fander and Bonomi into the task scheme. So where you can select few collective variables and use parallel bias applied on that, and we find that it's pretty good and very rapidly converging and much better performing than the conventional tasks where you apply normal metadynamics bias. Okay, so that's what I'm going to show you here. So this is an example of alanine pentapeptide. We have 8 collective variables. Okay, and these are projections of various projections of this 80 surface. And what I'm showing here is the exploration efficiency, like I have calculated before, where 8D surface has been decomposed into 6 by 6 by 6 by 6 by 6, like 6 power 8 grid points, and basically counting how many grid points is visited as a function of time. So even in 2 nanoseconds per umbrella window, you can see that this new approach is able to sample 50% of this 8D surface. Okay, but the conventional task is less than 40%. But of course, both these approaches are still good in 15 to 30 nanoseconds. You actually sample more than 80% of the 8D surface. Okay, so that is really remarkable. And you can see that the free energy of barriers converges very quickly, but what is more exciting is that even you can look at the free energy of these second order saddles, and this is just a test to show you that it's doing a pretty good job. And I should say that these free energy surfaces are constructed using artificial neural network, using the technique which Mark has already shown. So I'm not discussing that technique here. So that gives you kind of an extra I mean, it's extra benefit, because it helps you to smoothen the landscape, and then you'll be able to kind of measure the free energy more kind of accurately than otherwise that you have, but because otherwise it will be very smooth, noisy. You can imagine I'm talking about 8-dimensional distribution, and it's to converge that 8-dimensional distribution is really painful, and I mean, it's even to store that is almost impossible. So again, I want to show you here in 1 nanoseconds per window. Okay, we have sampled like 42% of this 8D surface. In 2 nanoseconds per window, we have 57% of efficiency. And I mean, as I told you that we run these windows parallelly, so it's not like one window after the other. So that means it's really, you know, really useful for us to explore such high dimensional landscapes. So of course, TAS is slightly less performing, and I'm not comparing other techniques because they are not anywhere close. Okay. So you can find, I will post these links again. We have some hands-on tutorials for doing tasks using Plumed. So I'll give the link, and also you can look at the lecture materials where these theories is discussed in detail, especially you know, Mark lectures is also there, where he will discuss about how this TAMD you know, reweighting can be done and so on. So this will be useful for everybody to understand the technique that I have also discussed. The first paper is this, where you will get the basic idea of the TAS approach, but it has started from this original paper in Journal of Computational Chemistry 2016, where we presented why it is important for us to basically you know, take the system, drive the system from one basin to the other without the umbrella restraint. You know, the system will start diffusing away, and we won't be able to have quickly see what we want to see. Okay. I also just wanted to add one point which I missed here, is that these I mean, from 8 to 15 umbrella windows, okay, whatever we have used these CV7 to CV24. So these collective variables were added explicitly only for these umbrella windows 8 to 16. Okay, for others it's not needed because the drug is already inside the active site. We don't need to bother about how they move around the protein. So that's the advantage of TAS, because when you see that, okay, you need an additional collective variables, you can throw it in, and because you're anyway getting the slice distribution and looking at the free energy on a projected space of your interest. So these are not going to matter. So you can change the orthogonal or transverse coordinate as you like, and keeping the important coordinates where you would like to look at the free energy at the end of it, at the end of the calculation, right? You can retain them. The rest can be changed. Okay, and that really, I think, is one of the thing that I really like in this technique, especially to look at some of these complex processes. With this, I will stop, and I'd like to thank my students, Shalini Avasti, Venkat Kapil, who started this project, then Abhinav Gupta, Shivani, and Ramsha, who are working those parallel bias metadynamics. Anji Babu's work I have not discussed, but he's going to show you a poster where he's going to look at much more complex systems. So Shubhendra Tripathi worked on the drug binding, unbinding. Asit Pal and Suraj worked on mean force approaches and reconstruction of free energies using machine learning. Then I thank Motoyuki Shiga, who's his discussion with him inspired me on the mean force based task reconstruction approach. I have benefited a lot from Mark Tuckerman's discussion with him, but I have to explicitly thank him for encouraging us to use GGMT, which solved all the crisis that we were facing, and also Dr. Curden, who shared the code of GGMT with us, which we implemented in GROMACS and in Plumed. Thank you so much for your attention, and I'll be happy to take questions.
Thank you, Nishant, for your excellent talk. So there are a couple of questions in the chat box. We'll first take them. We have about 5 minutes, okay, to discuss questions. The first one is from Savoni. Savoni, would you like to ask, or should I read it from the chat box?
You please read it, no problem.
Okay. Yeah, okay. I will read it. I will read it. Yeah. Okay. So how big a system can you handle at present? Has TAS been tested free energy of intrinsically disordered protein? Yes, one of my students, Anji Babu, has tried on that. He can share some light on that during the poster session, but he's not presenting that work right now. But we are looking at protein folding problem. So we are working with Mark also on this, on protein folding issues, how to use TAS for that. So we have been successful, but we hope that in a couple of months we'll be able to show you some results on that. Some initial results can be shared with you during the poster session.
Just a quick question. When you talk about that ligand solvation in that high dimensional problem that you talked about, what exactly are you plotting there? I mean, ligands, what is the quantity that you talk about?
You mean the free energy you are talking about, or
yes, that is
so
a setup 3.
Yeah, this is the free energy. Yeah, sorry, I might have missed it saying that. Yeah, this is the free energy as a function of 2 collective variables. We have 24 collective variables actually.
No, I understand that. I just want to understand what your ligand solvation CV is.
Okay. All right. Okay. So what happens is that so we wanted to at the bottleneck of the protein entry, right? I mean, where the ligand is just about to enter the protein. That's where all these complication happens, right? So you have ligand solvated by water, and we would like the water molecules also to diffuse a little quicker so that it can also sample other configurations.
Okay.
So what we do is ligand coordination number of ligand to solvent, the whole solvent in the system. So that number varies. It's just for boosting the sampling. Yeah.
Okay.
The same thing with other collective variables also. These are just kind of a booster coordinates. Yeah.
Okay. Thank you.
Okay. Nishant, the next one is from Jagannath.
Right.
The question is, please shed some light on how you have integrated the neural network to get a smooth free energy surface.
Oh, okay. So, all right. I think I have this slide. Otherwise, it's also as a poster. Yeah. So here it is. Yeah. So, Mark, I guess this is the right reference. Guess this is a 2007 PRL. Yeah.
That's the one. Yeah.
So what Mark has shown is that when you have to handle this high dimensional landscape, it's better to, I mean, there are 2 things which is crucial. One is these techniques which are based on high temperature. It explores the surface very quickly. So then at the end of the day, you get a noisy surface, right? On short time simulations. So you want to smoothen it quickly so that you can analyze the surface better. And you also need an analytical expression so that you can compress this whole data. Otherwise, storing this whole thing on a grid is practically impossible, right? I mean, because it requires a lot of data. So what we do is we have a coarse grid on the free energy surface. So like, let's say 6 into 6 into 6 into 6 into 6 into 6, like that. Okay, and then we calculate the free energy on these grids and use that as the training for predicting the free energy on any other value of the collective variable space. So the training, the input are these collective variables and the output is the free energy. And then you can use any value of collective variable, it predicts the free energy at the end of the day. So that's
fine. I see that Mark has a question. Mark?
Yeah, I think
it's actually just a comment. So it's great that, of course, you can run the task simulations. Each window is a parallel thing, and you don't have to do these things in serial. And of course, when we're comparing to, I guess you called it like a one window method, right? Like TAMD, where you just run the one trajectory. But we probably should do just one comparison where we simply run, if you have n umbrella windows, you can do n, let's say 33 independent TAMD runs just from different starting points. I just run them in parallel, and then that would be absolutely equivalent to a test simulation, right? Where you say, okay, there's certain number of nanoseconds per window, certain number of nanoseconds per trajectory, and then do that comparison and just see how they stack up.
Right. Yeah, exactly. Yeah, but the real advantage of this is to really keep the system on the top of the hill for a long time, so that even 1 nanoseconds per window is good enough to sample, actually, right? So I think the lower part of the basins I think they converge quickly, but anything more than that, I think that's where the task comes actually. Yeah, so
that could well be. Yeah, I don't want to say that I know what the outcome of that comparison would be. I have no idea, but we should do it. Yeah,
exactly. Yeah. Thanks, Mark. Yeah.
Okay, I think fine. So I see there is one question from Arnav. Arnav, you can put your question in the chat box and Nishant will reply to you. So with this, I think let us thank Nishant again for the wonderful talk.
Thank you, Amalendu. Thank you so much.
So we'll move to the next talk, which will be given by Amish Patel from University of Pennsylvania. Amish is going to talk on how do antifreeze proteins inhibit ice formation. Amish?
Yeah, we can see your slides.
Thank you, Amalendu. I want to actually start off by thanking all of the organizers for bringing us together in these strange times, right? I know that this has been one of my favorite conferences. The last conference that I attended in Agra was just an absolute blast. And I know that, you guys have to probably this is the third time, right? So there are 3 times as much work in organizing this conference, but I'm sure it's going to be amazing if the talks that we've heard so far are anything to go by. So thanks a lot. All right. So today I'm going to tell you a little bit about antifreeze proteins, which are this amazing class of proteins which make life possible in frigid environments. Right? These proteins have evolved in a variety of organisms, from fishes to insects to even plants. And they prevent organisms from freezing, the water in their cells from freezing. And they do so at concentrations of less than 1 weight percent, right? Typically small fractions of a percent. If you contrast this with the antifreeze that we put in our automobiles, in our cars, in cold climates, they have about 40% of the additive, right? So 40% versus less than 1%. And so the way these antifreeze proteins are able to inhibit ice formation is that they essentially seek out and bind ice in a vast excess of water, right? So on the right here, what I'm showing you is an experiment where GFP tagged AFP is binding and completely passivating a growing ice nucleus, right? And so since AFPs were discovered some 50 years ago, it has been a topic of tremendous discussion and intrigue. That how is it that these molecules are able to bind ice over water, right? If you think about it, water and ice are of course chemically identical, but they're also very similar from a structural standpoint, right? They both are characterized by tetrahedral networks of hydrogen bonds. And so this is sort of the feat that AFPs are able to accomplish has widely been touted as one of the most challenging molecular recognition problems in biology, right? Recognizing ice over water. And so how is it that these AFPs are able to bind ice? Well, given that really the only difference between ice and water is long range order, early suggestions centered around lattice matching, right? So the idea was that perhaps these AFPs present polar moieties that can hydrogen bond with water molecules in ice, but they present them in perfect registry with the ice lattice. And it is perhaps in this way that AFPs are able to preferentially bind ice, right? Once crystal structures of AFPs started to appear, people realized that in some cases, indeed, there are polar groups on the ice binding sites of AFPs that can be in registry with the ice lattice. But there are often a bunch of non-polar groups that are observed on the ice binding sites as well, right? So, for a molecule that wants to bind to ice, what role are these non-polar groups playing? Moreover, it was recognized soon thereafter that the chemical template presented by the ice binding site is remarkably finicky, right? So if one of the polar groups is mutated into a non-polar group, or vice versa, one of the non-polar groups is mutated to a polar group, that completely destroys the ability of the AFP to bind ice, right? So, this raises a number of interesting questions, right? So what is it about this chemical template that allows AFPs to bind ice? Clearly, they must perturb the nearby water in some well-defined ways. And so in what molecular signatures of these hydration waters might the icephilicity of the underlying AFP surface be hidden, right? And why is it that these these ice binding sites, the chemical template presented by them, why is it that they're so remarkably finicky to small changes? So these are all really interesting questions, but it turns out that the clues on how to answer these questions are contained in the seemingly unrelated problem of hydrophobicity. Right? This is to do with whether surfaces like or don't like water. In principle, this should not have anything to do with ice in antifreeze proteins, right? But it turns out that in just a couple of slides, I want to tell you a little bit about some of our work on hydrophobicity, which will turn out to be very helpful in thinking about AFPs and how they're able to bind this. Right. So at the end of this 2-slide detour, if you're left wanting to learn more about hydrophobicity and how we can what kind of things we can learn. I just wanted to sort of quickly flash this recent review article on hydrophobicity that we've written that you might enjoy reading about. All right, so what I'm going to tell you about is the behavior of water at hydrophobic surfaces and how it is different from behavior of water near hydrophilic surfaces. And once again, right, this is what will help us think about ice. So this is a little bit of a detour, but this will be useful. So I'm going to think about water near hydrophilic self-assembled monolayer surfaces that are terminated with something like the hydroxyl group, and contrasted with hydrophobic surfaces that are, say, terminated with something like methyl group. And we're going to focus on water molecules in this kind of an observation volume, cylindrical observation volume near the surface, right? In particular, I'm going to ask how easy or difficult is it to displace water molecules from the surface? What is the free energetic landscape within which these water molecules live, the number of water molecules in this observation volume? And this is what this landscape looks like, right? So there are about 100 water molecules on average in a volume like this. And regardless of whether we have a hydrophobic surface or a hydrophilic surface, we have roughly the same number of waters. The behavior near the mean is roughly very similar as well. What's really different about the behavior of water near these two surfaces is that when you start to have large deviations away from the mean, we'll start to look at low density fluctuations away from the mean, then the water near the hydrophilic surface has a parabolic free energy landscape. The fluctuations are Gaussian, whereas the water near the hydrophobic surface displays fat Taylor-Swift probability distribution. The ease with which water can be displaced from near the surface is substantially greater than that near a hydrophilic surface. Okay? And the implications of these differences are felt the most strongly when we apply some kind of an unfavorable perturbation to water molecules near the surface. And so let's look at this example where we apply an unfavorable linear potential, which couples to the number of waters in this volume. And phi here represents the strength of this potential, right? So the more I crank up phi, the more unfavorable it is for waters to be in the volume. And so waters systematically start to leave the volume. But the manner in which they do so is very different, right? For the hydrophilic surface, the waters leave gradually, slowly leave the volume, whereas near the hydrophobic surface, the behavior is very much collective and switch-like, right? So you have all of them leaving at once. And so the key here, that things that I want to take away with is that low density or vapor-like fluctuations are enhanced near hydrophobic surfaces. And I want you to think about hydrophobic surfaces as not necessarily surfaces that don't like water, but surfaces that have a preference for water vapor over liquid water, right? So you could also think of them equivalently as vapor-philic surfaces. So vapor-like fluctuations enhance near vapor-philic surfaces. And this situates the interfacial waters at the edge of a dewetting or a liquid to vapor transition. Right? And in fact, these ideas that I've described to you using these very simple surfaces, it turns out they apply equally well to incredibly complicated systems, things like proteins and the entire hydration shells of proteins. If I play the same game that I did in the previous slide for the self-assembled monolayer surfaces, if I apply an unfavorable potential to water molecules in the first hydration shell of this protein, we see that the response is very much like that of a CH3 sand, right? It's sigmoidal. As I crank up the potential, all of the water molecules sort of collectively dewet the hydration shell, right? And this, it turns out, makes the patches on the surface of a protein very sensitive to perturbations. So as an example, if we take this particular protein and swap two of its amino acids, the locations where these two amino acids are, then that can change the hydrophobicity of this particular patch by almost 20%. And moreover, being able to identify the regions of the protein that dewet most readily and are therefore the most hydrophobic, it turns out that these most hydrophobic regions that dewet in response to an unfavorable potential can also teach us a lot about the regions of the protein that mediate their interaction. So this particular protein, turns out, dimerizes through this particular interaction interface, and it forms a protein-protein interaction interface. And so, you know, the main message that I want you to take away from this slide is that you know, protein surfaces actually behave remarkably similarly to uniformly nonpolar hydrophobic surfaces. The water molecules in their hydration shells are sensitive to perturbations, undergo collective dewetting. Sites on the or patches of proteins are very, the hydrophobicity of protein patches is very sensitive to the chemical template that it presents. And the most hydrophobic patches of proteins tend to mediate their interactions. Now, it turns out that all of these features are also found in AFPs, in antifreeze proteins, right? So we're going to end our detour and come back to AFPs. And, you know, based on our understanding of hydrophobicity or surfaces, whether they're self-assembled monolayers or proteins, the fact that hydrophobic surfaces feature are characterized by the ease with which low density or vapor-like fluctuations can be observed near them, right, prompts us to hypothesize that perhaps, you know, if ice-like fluctuations should correspondingly be enhanced in the isophilic hydration shells of antifreeze proteins, right? So just like vapor-like fluctuations are enhanced in the hydrophobic or vapor-philic hydration shells of normal proteins, perhaps ice-like fluctuation should be enhanced in the hydration shells of AFPs, which are isophilic, and thereby it should situate the AFP hydration waters at the edge of a freezing transition, right? Making these waters and particularly sensitive to the template presented by the AFPs. So this is a sensible hypothesis. Making it is easy, but testing this hypothesis turns out to be much more challenging, right, than positing it. Certainly, you know, sampling the rare ice-like fluctuations near surfaces, it can be challenging and involves biasing appropriate collective variables, order parameters, which you know, we're gonna. I won't go into too many details regarding those order parameters, but I'll say that they're based on spherical harmonics. In particular, we build off of Leshner and Delago's work and using local orientational order parameters, right? But even if we can bias orientational order parameters and sample rare ice-like fluctuations near AFP surfaces, right? to test a hypothesis of this nature, right? That you know, say ice-like fluctuations are enhanced near ice-philic surfaces and suppressed near ice-phobic surfaces. If I want to test this hypothesis, I need a library of surfaces that span a range of ice philicities, right? How do I get such a library of surfaces? That itself turns out to be non-trivial, right? What makes a surface ice-philic versus ice-phobic, no matter how simple or minimalist the surface is. When it comes to thinking about hydrophobicity and hydrophilicity, the same question had a very simple answer. All you had to do was tune the polarity of the surface, and it makes it hydrophilic. Right? But what knob do you turn to make a surface go from being ice-phobic to ice-philic? And that turns out to be an interesting question that again, when we first started thinking about this, it wasn't clear what the answer should be. So we started with the simplest possible surface that we could imagine. We started with ice itself. The one thing that we do know is that the surface of ice should like ice. Right? And so we took the molecules that are part of an ice crystal and position restrain them to make what we like to call a pseudo ice surface. Right? And then to sort of try and vary their properties, what we did was we systematically varied the polarity of this pseudo ice surface to generate a sort of family of these pseudo ice surfaces. Okay. And what we found, and then once we had this family of surfaces, we then set out to systematically characterize their ice philicity. And to do this, we made use of a method that we have recently developed to characterize the hydrophobicity of surfaces, and in terms of the traditional measures like contact angle or wetting coefficient. So we've adapted this method to now thinking about ice philicity. What is the preference of the surface for ice over liquid water, right? And I'm going to characterize that using the wetting coefficient, which is essentially cosine theta, or the difference between the solid liquid interfacial tension, solid ice interfacial tension relative to the ice water surface tension. Okay? So the idea behind this method is very simple. We basically take the surface that we are interested in, and we start with a configuration like this, where you have water or the two phases, in this case, ice and water between the two surfaces of interest. And we wet the surface with ice, meaning we move this liquid water interface forward so that more of the surface comes in contact with ice and less of the surface is in contact with liquid water. Right? And so if we simply think about this very simple process, the free energy associated with this process should be related to the change in the surface tension as you go from having solid ice interfaces here to solid water interfaces before. Right? And if we can figure out if we could carry out this process, figure out what the free energetic cost of carrying out this process is, and also figure out the area of the surface that we have wet with additional area that we wet with ice, then we can infer what the wetting coefficient or ice philicity of the surface should be. Right? So that's the basic idea. Here, how it works in practice. Here's how it works in practice. These gray surfaces that you see are the pseudo ice surfaces that we want to study. We additionally have these boundary surfaces, which all they're there to do is to break the symmetry and make sure that we're going to have ice on the left-hand side of that simulation box and water on the right-hand side of the simulation box. Right? And then in this probe volume, in this observation volume V, we are going to apply a biasing potential that tries and establishes a certain number of ice-like waters. So the collective variable is the number of ice-like waters that we observe in this volume V. And so when we turn on a potential of this sort, what we see is that ice starts to form, and more of the surface that we care about comes into contact with ice. Right? There's a bunch of liquid waters everywhere, but they're hidden for the sake of clarity. Right? And so we can systematically vary this M star and systematically wet more and more of the surface with ice. And as we do that, we see that the free energy is linear in M star, and correspondingly the interface also moves linearly with M star. Right? And so by taking the ratio of these two slopes, we can then infer what how much the surface likes ice, what the corresponding wetting coefficient is. And so for this particular pseudo-ice surface, for which the charges on the surface have been scaled by a factor of 0.75, it turns out that the wetting coefficient is 0.5. This means that the surface likes ice over water, and the contact angle is roughly 60 degrees. We can carry out the same exercise for our entire family of pseudo-ice surfaces. And what we find is that as we reduce the polarity of the surface, of course, when we start with essentially the position restrained ice surface, it's perfectly icephilic, has a K of 1. But as we start to reduce the polarity, the icephilicity of the surface starts to drop quite rapidly. By the time we reach half the charges, half the polarity of the ice surface, we have basically a neutral surface that likes neither ice nor water, or it likes them both equally. Further reducing the polarity leads to a further decrease in icephilicity, or it results in icephobic surfaces. But the decrease in icephilicity is much more gradual, beyond 0.5, polarity charge scaling of 0.5. And so at this point, I'd like to emphasize that the fact that a non-polar surface likes liquid water more than ice, or is icephobic, is not at all trivial, right? When we first started thinking about this, it was not clear to us whether a non-polar surface, you think that it should not like water, but then it should not like ice either. So, it's not clear why it should like one more or less than the other. Right? So these results tell us that non-polar pseudo-ice surface actually is icephobic. It prefers liquid water over ice. Interestingly, these two regimes that we see, a sharp drop in icephilicity and then a more gradual drop in icephilicity, has to do with a change in the water molecules between the surface and ice. So you see these water molecules in pink here. These are the water molecules I'm showing you here. For surfaces with high values of polarity, these water molecules that bridge the surface and the ice are all in registry with the ice lattice and call them anchored. Whereas for the mostly non-polar surfaces, these water molecules shift and occupy the centers of these hexagons, right? And this change in the configuration is just corresponds closely with this change in the sensitivity of the icephilicity to the polarity of the surface. At this point, this is very interesting. We had already now accomplished what we set out to do, which is have a library of surfaces with a range of icephilicities. But we were curious as to how surfaces that were not lattice matched with ice, how might they behave, right? If I had a polar surface that was not lattice matched, would that be icephilic or icephobic? And as I change the polarity of such a surface, how might its icephilicity change? Right? And so what we did is we created a complementary set of surfaces where we basically took a configuration from liquid water and position restrained those water molecules. We call that a pseudo water or pseudo liquid surface. And then again, we varied their polarity systematically to obtain a family of pseudo liquid surfaces. And what we find is that all of the pseudo liquid surfaces are icephobic, and they all have roughly the same value of the wetting coefficient. They're all roughly equally ice-phobic. So the most polar pseudo water surface is just as ice-phobic as the non-polar lattice match surface. And so there's this very interesting discrepancy or difference between the way lattice match surfaces behave and non-lattice match surfaces behave, right? So yeah, non-match surfaces are ice-phobic, but their ice phobicity is insensitive to polarity. And then non-polar surfaces, whether they're lattice matched or not, have roughly the same ice phobicity. So these results are sort of, they echo this increasing sort of consensus that whether a surface is ice-philic, ice-phobic, whether it's able to nucleate ice, that tends to depend sensitively on the molecular characteristics of the surface. So with this, set of surfaces that span a wide range of ice phylicities, we now set out to test our hypothesis that ice-like fluctuations should be enhanced in the hydration shell of ice-philic surfaces, right? And to do so, we once again we did a calculation very similar to the one that I showed you early on for the SAM surfaces. We look at an observation volume near a pseudo ice surface and ask what is the free energetic cost for ice-like fluctuations near the surface, right? And what we observe is that as we make the surface more and more ice-philic by increasing alpha, that it becomes easier and easier to observe ice-like fluctuations near the surface, right? So the hypothesis that I pose is indeed true. And it now provides us these ice-like fluctuations and the ease with which they can be observed near a surface can now be used as a molecular measure of the ice philicity of a surface, right? And now you might say, well, for these surfaces, you already knew what their ice philicity was, right? And you'd be right, but the true advantage of a molecular measure of this sort is that we could apply it equally well to more complicated surfaces like those of antifreeze proteins, for which things like contact angles or wetting coefficients are not even well defined, right? So you could ask the same question: if I take a particular region of the AFP and systematically induce ice-like fluctuations, how easy or difficult is it to stimulate ice formation near the protein surface? And the ease with which ice can be formed will tell me something about how ice-philic or ice-phobic that region of the protein is. And so that's exactly what we did. We took an AFP called SBW AFP, for whom the ice binding site is known. We imagine that this ice binding site, which has been determined experimentally through mutagenesis experiments, should be ice-philic. We can run our kind of calculations and characterize the free energetic cost for nucleating ice here. And we can repeat the same exercise for the rest of the protein, the non-binding, non-ice binding site of the protein, right? And we find that indeed it is a lot easier to stimulate ice formation near the ice binding site. And the ice binding site, in other words, is more ice-philic than the rest of the antifreeze protein. We can play the same game in reverse as well. We can take the antifreeze protein and ask, what might its ice binding site be? Right? Through what region of the antifreeze protein will it bind ice? And the way we answer this question is we take the entire hydration shell of the AFP and we apply a bias that strives to nucleate ice in the hydration shell. And it turns out that the regions of the AFP that readily nucleate ice when applied in the presence of such a biasing potential, that I'm showing the ice that is nucleated in blue here. And so our hypothesis would then be that these are the regions that are the most ice-philic, and thereby the regions that allow the AFP to bind to ice and passivate its growth. It turns out that in this particular case, mutagenesis experiments have been done. And so the orange amino acids are ones which, when mutated, completely abolish AFP activity. Whereas the purple is a control mutation which doesn't change AFP activity at all. And so we are very happy to see that when we nucleate ice in the hydration shell of this AFP, it forms it near the orange residues, but not near the purple residue. And so this lends confidence to our ability to actually predict ice binding sites of AFPs, which is very exciting because, of course, mutagenesis experiments are very onerous, right? And so the last thing I'll say is very preliminary results that we have that have to do with looking at the ice binding sites of a variety of AFPs, which differ in their activity. So different organisms have evolved different AFPs that are able to suppress or ice nucleation to different extents of supercooling. Right? The hyperactive ones can be supercooled the most, and the hypoactive ones the least. And so what we found is that the more the activity of the AFP, the more icephilic its ice binding site seems to be. Okay. So with that, I'd like to conclude. What we observed is that for lattice match surfaces, their icephilicity tends to increase with polarity, and the dependence is strongest for relatively polar surfaces. Whereas the non-matched surfaces are quite icephobic, and their icephobicity seems to be independent of polarity. Right? And so hydrophobicity may provide a route to icephobicity, but icephobic surfaces need not be hydrophobic. They can be hydrophilic and non-lattice matched. And extending these observations to AFPs, we found that even complicated antifreeze proteins display enhanced ice-like fluctuations in their hydration shells, which situate them at the edge of a freezing transition and enable them to recognize ice. Right? The patches of AFPs that freeze in the presence of a favorable perturbation also tend to mediate their interactions with ice. And our very preliminary results suggest that the thermal hysteresis activity of an AFP may be related to its icephilicity. So I know I'm almost out of time, so I'm going to acknowledge the people who did the work and the funding and stop here and answer any questions if there's time.
Thank you, Amish. Thank you for the very nice talk. Yeah, we have time for a couple of questions. So the first one would be from Biman. Biman, could you please unmute?
Yeah, so it was not working earlier.
Okay.
So great talk, Amish. I'm just thinking that this fluctuation you are talking about, ice-like water molecule fluctuations around the surface of antifreeze proteins, but different antifreeze proteins, let's say the one you have taken type 2 and insect, but type 3 antifreeze protein has a very different surface. It is mostly hydrophobic, and we have seen that they actually prefer to form clathed-like water rather than ice-like. So whether you have actually tried your method for type 3 AFP or not?
Yeah, that's a great question. So this guy OP-AFP, and the one that I'm showing you here is actually a type 3 AFP from ocean pout. And we do see that they behave sort of very much in line with our expectations. Now, we haven't looked carefully at what kind of what the sort of bridging waters do, right? Whether the binding motif is an anchored clathidic one or a different one. But in terms of the ability of the ice binding site to nucleate ice in the presence of a favorable potential, the different classes of AFPs seem to be behaving in similar ways.
Okay. Thank you. It's great work.
Okay, thank you, Biman. Andrew?
Hi, Misha. Beautiful talk. Really enjoyed it. I just had a question on. I really liked your sort of templating versus non-templating surfaces, and this sort of like glassy water, sort of being sort of phobic the whole time. I'm just wondering if you tested an unstructured surface, so something that's atomistically smooth, just sort of a smooth LJ wall type potential. or if you could speculate on how that would behave that has sort of no templating behavior.
Yeah, so we've looked at an LJ surface, just a non-polar LJ surface, and that is also icephobic, as you would expect, right? But we haven't tried. And then the other thing that we've done is we've sort of loosened the position restraints, right? Which again, makes them it makes them floppy. They're probably still somewhat structured, but much more floppy. And they are, whether you start with an icephilic, pseudo ice or pseudo liquid surface, both classes, when you sufficiently loosen the position restraints, they become icephobic as well.
Okay, all right. So I don't see any other questions either in the chat box or through raising of hands. So with this, then I think let us thank Amish for his excellent talk, and we'll move to the next talk, which will be the last talk of this session. The last talk is going to be given by Jagannath, Dr. Jagannath Mondal from TI for Hyderabad. He's going to talk on decoding metastable states in folding and recognition. Jagannath.
Yeah, can you hear me?
Yeah,
okay,
sure.
Okay. And okay, so thank you very much for providing a good session today. And what I'm going to talk about is something that we learned from the last year and try to build something over the last few years to see whether we can also train ourselves to on that particular direction. So keeping in the theme of many of the talks today's sessions where we have talked about collective variables, so we are going to mostly think about whether we can decode many transient metastable states that we generally see in two important biomolecular processes, for example the protein folding and small molecule recognition to the protein using collective variables. So what I think I'm going to do is somehow my card this is not moving, but anyway, so the thing is that as has been already discussed in this last few seminars today, and this audience is also quite well aware that collective variable is something that is a tool that whether a chemist or a physicist or any of my peers here who is thinking about thinking molecular simulation, we cannot avoid. And this is actually necessary, convenient, and crucial so that we can, look at or reconstruct, the underlying processes that is going on at a low dimensional surface. So, and as a result, one need to really project most of the cases, the underlying processes along a free energy surface, and we need collective variables. And in most of the cases, those collective variables, at least for inspection, should not be too many, and it has to be restricted to definitely much less than the total number of degrees of freedom. At the same time, as it was very clear from Nissan's presentation, that it also is basically forms the heart of enhanced sampling, and at least the most prominent enhanced sampling techniques, which is most popular, which is metadynamic simulations and umbrella sampling. These need collective variables to start with, so that we can bias things at a particular directions that we want. Okay, the question that actually also happens many times, what we also come up with, for example, what we found in one of our earlier work when I was doing a postdoc with Bruce Byrne, that you need in sometimes very non-intuitive collective variable, like number of water that is present inside a protein cavity, along with, let us say, distance, to think about the solvation barrier that you might need to overcome for the ligand to get in the pocket. So this actually tells you the the complexity that actually we generally encounter, and that is why most of the time generally we have to choose a collective variable that is actually working for the process that is interested. So now the thing is that the way generally we are trained to think about collective variables has been for several decades is that we generally rely on our chemical intuition or researcher experiences, and as you saw in many of the interaction that we had in our chats today, we found that we have to really think about for the process a certain collective variable which which actually comes to your mind. Let us say you're talking about protein folding, you have to think about, let us say, whether fraction of native contact is good enough, or whether you need to think about radius of gyrations, or whether you have to think about center of distance, or even, as I already pointed out, the hydration might be an important perspective. So it actually never ends, and basically we always think about, these are the collective variable that actually is might have worked in previous systems, maybe it will work in your current systems. So that is one particular way to think about it. Of course, the researcher experience and chemical intuition is important. The other aspect that actually is becoming more and more popular, which has been also there for a long time, is basically thinking of in the terms of whether we can reduce the dimensionality of the systems, and whether we can project the data on a particular, let us say, non-trivial collective variables, and can we actually learn from those things. So this is also out there for a long time, and as everyone aware is that generally the linear projection of the data, which is quite quite common in our simulation community, that has been played an important role to reduce the dimension that we are talking about. So for example, the principal component analysis now has become almost like routine because of the many tools that is out there. And the other technique which is also has got prominence over the last few years thanks to Markov-State models and other techniques, and so time structure independent component analysis that was originally discussed by Vijay Pandey and Frank Nui independently, which is also called TICA. So these techniques has been out there for a long time, where we are trying to see whether one can think about a linear combination of many of the independent collective variables that we can think about as a optimal collective variable for this kind of processes. So what actually it boils down to that like we have to think about either approach like PCA or principal component analysis, where you are trying to think about a combination of input and coordinate which will maximize the variance of the data along a particular dimensions, and we'll try to project our simulation trajectory on that particular coordinate along which the dimension is getting maximized as far as the variance is concerned. But of late, which is becoming more and more popular, is that apart from dimensions which is going to give rise to a maximum variance, what we are really looking for is that we are looking for the rate determining step in a particular process. So many times the kinetically slow coordinate, that means along which the process that we are looking for, whether it's protein folding or a chemical reactions or a protein ligand binding, that is going to have the slowest component, that might also be more important. So in that particular regard, I think one of the key key approaches that has become pretty prominent over the last 8 or 9 years, which is also still linear in approaches, called time structure based independent component analysis, which is called TICA. So the idea here is that you are trying to look for a optimized projection along which the autocorrelation function of that projection is going to decay slowest. So as a result, by construction, you are going to get a collective variable which will still be a linear combination of set of collective variable that you started with, but it is by training the coefficients of those the linear combinations are going to be obtained such that the the autocorrelation functions of that particular projections is going to be slowest. That means it is going to decay the slowest. So this is something that we have also tested previously in earlier in 2018 or 19, where we tried to see that whether we can think about one of the most popular model system in for molecular simulations, which is called the C-terminal domain of GP1 hairpin and GP1 protein, and whether we can come up with a optimal low dimensional collective variable to study this protein folding. It's mostly because this particular system has been out there, and people have looked into the folding landscape of these things using many different traditional collective variables. So for example, some of them we are already putting here, which has been already present as a library. Let us say number of hydrogen bond that is present here, number of contacts that you basically make, which are native already in the systems, or you can also think about radius of gyrations or RMSD or number of water molecules. So what we thought is that why don't we try to think about an optimal collective variable, where we are going to focus on only these 5 candidate CV, but we are going to basically try to use this approach of TICA to come up with a a linear combinations of these collective variables, and we'll try to get the we'll try to project our simulation data on, let us say, the slowest 2 TICA dimensions, so that we can actually get an idea of how the projection looks like. All right, so that was basically the original idea. So first, what we found that if we try to take any of those 2 different CVs that we actually had present in our data, and if we basically use, let us say, set of replica exchange molecular dynamics simulated data, and if we project any of those 2 collective variables as a pair, we find that it's very difficult to see all the all the metastable basins that we are thinking about. But if we try to now think about these two different collective variable TIC1 and TIC2, which is basically obtained from TICA. And if we try to project it, we basically find that, in principle, you can actually come up with many different, metastable state apart from the unfolded and the folded state. And, one can actually also try to do Markov state models and create a Markov state model to even look at the kinetics from these particular things. And as a added benefit, what we found is that using these linear approaches, you can also, once you basically are prepared with this, the projections, you can actually also look at the, relative contribution of each of these coefficient that is present in this optimal CV. And that way we could basically at least, ascertain that, in these cases, maybe the number of native contacts or, radius of gyration for this particular protein would be crucial to basically, get the most of the, important states out there. So this is which we basically found that maybe a systematic way to figure out how to think about the, collective variables. But here, one thing that actually we had is that, if we really think about to start with the initial collective variable that we started with, like that is the number of hydrogen bonds or native contacts or radius of gyration or RMSD, all these things are to some extent still, biased by the user intuition, because these are also, traditional choices. So what we, what we thought is that can we actually try to, think about pretty large dimensions, and at the same time, can we go beyond the, this linear dimensional reduction technique that is out there, and can we try to see that whether there is any better way of thinking about it, even more unbiased approaches. So what we thought is that, the problem is that we are dealing here, that the data that is basically the simulation trajectories, which are often multi-microsecond currently, is quite stochastic, and by inherently, by training, it is by nature, it is actually completely non-linear. So maybe the non-linear transformation of this kind of data might be a more generic and more possible promising way forward. So that in that particular aspect, what we are finding in the literatures of the last 5 years, actually the approaches of artificial intelligence are becoming more popular, so that we can optimize the collective variables. So as a result, this approach of machine learning, and most importantly, the deep learning is becoming, it's becoming very, very common these days. So what we thought is that, why don't we, try to think on that particular line? So what we thought is, one of the way that we can think about, we can try to use this, these approaches of artificial neural network, and especially the, the approaches of autoencoder to, think about the dimensionality reduction. So what we, just wanted to introduce to those who are actually not aware of artificial neural network. So this is actually, a set of, it basically kind of, inspired from the, biological, neuron that we generally know of, which basically has many different, nodes that is basically, initiated, and they are actually interconnected by a very complex network, and through which you basically try to produce the output, which is going to be on the other side. So now, what actually we thought that, you will basically have this kind of, interconnected layers that is present there. So the input and output can be different, but what we are trying to basically getting inspiration from is the work by Hinton and his co-worker, which actually showed that if you try to think about, let us say you are trying to reproduce the, let us say, a particular input, which is, let us say, the human face, and we are trying to reproduce the same thing. So one can come up with an encoder which is kind of trying to encode itself, which is like a self-supervised neural network. So we'll have multiple layers in between them. So we'll call them, encoders, and then we'll basically try to reduce the number of layers that is present. And those layers are going to be basically finally compressed in a bottleneck layer. And then what we are going to do is that we're going to slowly again decode by increasing the number of dimensions. And finally, we're trying to see whether we can generate the output image. And we'll try to do this exercise until which the difference between the output and input becomes almost minimal. So that is what I think we are going to train as a loss function, and we're going to see whether we can actually optimize the process such that the loss function can saturate to a smaller value. So that is one particular approach is that is present. So this is, we thought that why don't we think about that particular line. So what we decided is that instead of thinking about any of those user guided collective variables like number of hydrogen bonds or native contacts or radius of gyrations, why don't we take even more fine grained input coordinates and try to see whether we can come up with something. So what we decided, to be more specific, let us say we are talking about a beta hairpin, and we basically have, let us say, a set of residues which is present there. So what we can do is that we can calculate the C alpha, all distances that we can come up with as an input layer. So let us say these are all D1, D2, D3, which are basically a large set of input distances, and one can generate these input distances from the molecular dynamic simulation trajectories that one can actually use, and one can actually calculate those input distances. So this will be a set of layers, and then what we are going to do as a as part of the algorithm of autoencoder, we are going to basically consider many different connectivity, and we'll have a set of weights which is basically provided by this W, and we'll actually have a bias factor, let us call this B1, and we are going to think about reducing these dimensions, and we can actually come up with, let us say, multiple layers in between, which will be the encoder layer, and let us say finally we are going to come to this particular our interest, which is the bottleneck layer, and let us call them chi1 and chi2. And what we can do is that we can write down the the function of chi1 as a function of a nonlinear function of weights and biases, and this f, which is generally known as activation function, so that can actually impart the nonlinearity that we are looking for. And then once we are done with generating this bottleneck layer, then we are trying to again decode and trying to come back to the original input layer, which is again the set of input distances that we actually had from molecular dynamics simulation trajectory. So what we generally do is that this this particular entire network, we now try to optimize such that we can train such that weights and biases, all these factors can be optimized so that we can actually minimize the mean square error between the predicted and the the input coordinate, and that way we can actually try to see whether we can get something out of it. So what we actually did is that with this particular approach, we thought that why don't we first try to learn for a very simple system for which we have worked extensively. We initially started working on in this system when we were looking at polymer collapse in a osmolyte and all these things, but in this particular cases, this is just an example that we thought that for this particular system maybe we can learn out of it. So this is simple 32-bit polymer, and it's very simple, and as a result, for this particular system we already knew that radius of dilation is a very good collective variable for this particular system. So what we thought is that instead of knowing whether radius of dilation is a good collective variable, if we instead of putting that as an input, why don't we consider all inter-beat distances that is generated from molecular dynamics simulation trajectories as my original input, and then why don't we basically try to generate an autoencoder framework where you are slowly reducing the dimensions by optimizing the weights and biases, and try to recreate this original initial input that we had as an output. And this is basically what we found, that you can actually use this that as a result, what we can basically do is that we can try to look at as a function of the number of iterations that we doing this process, how the loss function is behaving, and we do see that it basically decays quite rapidly if we basically can if we basically try to look at it. And then essentially what we can do, we can actually then look at, after this actually has optimized, we can actually look at what is this this embedded bottleneck dimension look like. So we are now going to project our simulation trajectory, let us say, along this coordinate, and this chi is basically our projection as a function of time along those bottleneck layers, and RG is basically for this particular polymer has been already known to be a good collective variables. And what we find is that very interestingly, this particular collective variable chi actually is basically following the similar kind of time course as the radius of dilation is taking. So this actually tells you and gives us a confidence that this particular newly developed reaction coordinate, which might be very abstract coordinate to start with because it's a nonlinear function of the inputs, is still basically reproducing something which is already known to be a good collective variable. And the most importantly, what we can actually come up with is that we can actually look at different states, and we can see that all kinds of conformation this simple polymer is taking. And as a result, we thought that this might be a good strategy to think about future extension, and why don't we then try with our another system which is called GB1 beta polypeptide. So what we did is that in this case, as I told you, that it was not very well known to start with what will be good collective variable. So again, here we try to do the same exercise. We try to use the original input, which is as a all the inter-residue distance, inter-C alpha atom distance for all the all the data that we have, and we actually had already a fair amount of MD simulation trajectories, and then we thought that we can actually try to try to train it on an autoencoder so that we can reproduce that set of input residue distances to start with, and then we try to see whether we can come up with a projection in the bottleneck and try to project our data along these things. So we actually are what we are doing now is that we are trying to now project our simulation trajectory on a free energy landscape along the bottleneck layer that we obtain from this autoencoder, which is called chi1 and chi2. And what we found is that, most importantly, this particular chi1 and chi2 along this projection, we can clearly see many different, minima. The blue is the blue and the red is basically the blue is the local minima that we find. We do see that there are quite a lot of states which are first of all non-overlapping, and most importantly, what one can do is that one can actually decompose this entire free energy surface using this PCCA, and you can actually try to see that each of these state that we are trying to say as a minima, they actually come at a different location of chi1 and chi2, and that actually is something that we generally look forward to when we say that the collective variable is optimal. So this particular collective variable pairs, which is obtained from autoencoder, will be essential to basically at least making sure that we get multiple states which are actually not overlapping on top of each other on a free energy dimension. So there is no hidden hidden state that we are missing out here. And most importantly, if you try to let us say extract the conformations for each of these state, we do see that they are actually also as far as the secondary structure is concerned, or the overall the secondary structure of the topology is concerned, they are quite different. Actually, we can see that we can start from a completely unfolded state and we can go to completely folded beta sheets, and in between we can cover many of the interesting states which are actually distinct as far as the secondary structure is concerned. And that actually also gives rise to a very a clear free energy decomposition along two independent collective variables which are not generated from many of those pre-decided collective variables. So that actually also asked intrigued one question: how good is this particular collective variable? Can we quantify the optimality of this latent space CV that we are coming up from autoencoder? So one of the ways that the optimality of collective variable can be determined is something called this VAM score, which is basically called variational approaches to Markov processes, which was also defined by Frank Noe and his group, that you can actually try to provide a score to figure out the slowness of each of these collective variables and try to see whether the score is higher for a particular collective variable that we have come up with. So what we could do is that for GB1 we try to use the PCA using the same input coordinates, and we try to figure out that what is the result that we get here, and then we try to basically do the same thing for Tika and autoencoder, and for each of the CV that we generated, we try to calculate the VAM score, and we clearly found that the autoencoders are actually providing much higher score compared to the PCA and Tika. And most importantly, you can also try to develop a Markov model for along those those dimensions and try to look at the time scales. You will see that compared to Tika or PCA, especially in Tika, we don't even see that it is coming flat so quickly. In this particular autoencoder case, we do see that the time scales gets flattened, but the model reaches Markovianity very quickly. So that tells you that this is really a capturing a slow coordinate that we are looking for actually. All right. So then what we could do is that we could even try to use the same system by using the similar approaches on an application where you're looking at let us say protein which is going through folding and misfolding in two different solution, in one in neat water and one in the TMAO solution, which is the osmolyte. And we could see that we could capture that in presence of TMAO, many of the many of the state which is present as a metastable state are becoming less stable. That basically means that you can gain we can actually project along a particular collective variable which actually can show that this actually show you that TMAO can stabilize the folded state relative to the many of the other states. All right, and finally we actually could even scale these systems to even large system like cytochrome P450, which is among 450 systems. And here we could even try to figure out if I try to think about a complex conformational heterogeneity that this particular protein goes through between two state, open and closed, we could actually show that in a projection along chi1 and chi2, which is again we obtain from autoencoder, we can actually see that we can see multiple states which are actually non-overlapping and present in a different states, and it actually covers a wide range from open state to closed state, and we can get intermediate states also. So this actually gave a confidence that maybe these approaches of autoencoder that we are using for protein folding can be thought in terms of protein ligand binding as well. So one particular way that we thought that then what we can do is that we can use some of our recent result that we actually looked at for a particular protein ligand binding, where we basically looked at how a small molecule like benzene gets into the pocket. And fortunately, we actually had quite a lot of simulation trajectories, which actually captures the successful binding So this is plotted as a function of distance, as a function of time. And you could see that, we have a lot of simulation trajectories at our disposal, but we didn't really was more, intrigued by this particular observation that, in this particular system, we found that if we visually inspect, there are multiple pathways by which the ligand is going on. For example, in this particular trajectory, the ligand comes from, let us say, these two helices. But let us say if you just look at another simulation trajectory, in this particular case, it actually comes to, in a completely different pathway. So this idea of having multiple pathway to get inside the pocket is not so trivial, because generally protein ligand binding is known to have one single dominant pathway. So what we basically wanted to ask ourselves that, we do see an example here where we are finding that multiple, multiple pathway, but these are based on visual inspection. Now, can we basically train the simulation data and try to come up with a collective variable which will automatically predict this kind of multiple pathway? So what we basically try to ask ourselves, can we discover CVs which will basically display this kind of multiple pathways on a low dimensional landscape? So that is exactly, we thought that why don't we then try to build a similar autoencoder approach where we can basically consider a set of, input as a protein amino acid residue and the ligand distances. This is that all, let us say you have 164 amino acids, and you are talking about the distances, which is again 164 distances, and you already have the MD simulation trajectories. And we do the same exercise where you try to generate an autoencoder where you are reducing the number of dimensions on a bottleneck, which is chi1 and chi2, and basically trying to optimize the loss function so that you can get a very good neural network, and try to then use this chi1 and chi2 to project the data. So what we basically did is that we actually tried to project our simulation trajectory that you already have in our hand on this chi1 and chi2 that was generated from a very large input data sets. And we basically find that the surface, first of all, is produced to be very rough. And we basically can capture that there are, certain terrain which is unbound, as we basically see. And then we also find that there is completely bound pose, which is present as a red thing, which is the most stable one. And in between, we do see that there are small patches, which we are referring as an intermediate. Now, the question is that how do we see that these are intermediate? So what we can do, we can go back to our data, and we can project our kinetic simulation trajectory on top of this. So this is, let us say, one particular snippet. What you will see is that initially it starts from unbound state, and then it is going to basically go to one of this intermediate, and it will basically go to the bound phase. I will play it one more time. So you will see that in this case the ligand is coming from this pathway, and you can basically see that this particular CV is actually also showing that it will start from unbound state, it is going to one of those intermediate, and then finally reaching to the bound state. Now, if you basically use the same surface and if you try to project it on a different simulation trajectory to see whether this can also predict a different way of ligand binding or not. So this is basically the actual simulation trajectory where you can see that it is covering unbound to one of those intermediate called IN2. But here what we will see is that the ligand is spending now a lot of time between the pocket and this gateway. So you will see that this particular intermediate dynamical transition is very nicely projected along the surfaces. And if you basically wait for long enough, essentially you will see that just before it waits, it will jump to this particular the red bound basins without without delay. So it will basically tell you that this is actually a surface which is basically learning from very large input dimensions and trying to project it on a lower dimension, but essentially at least is generic enough to cover two different trajectories, which is known to have completely different pathway. So with that, I think I'm going to just conclude, but finally I'm just going to give you a teaser. So there is something that we are also trying to do and that you are going to listen from one of the talks in 17 December, where we are trying to see is that is it possible that we can put some supervised classification on this dimensional reduction to understand whether there is a binding competent state unique to a particular protein conformation. So that is something that I think Navjit is going to talk about in a later lecture. But finally, I think I'm almost wasting my time, so I'd like to conclude here saying that we try to propose a self-supervised autoencoder framework which is supposed to optimally discover the CVs, and we found that very fine-grained input as a residue level distances is actually can be trained on a neural network to come up with a very low dimensional complex surfaces, but which actually at least make sure that the states are non-overlapping, and you can even try to create multiple recognition pathway. So finally, this work is actually should be acknowledged, because the most of the this autoencoder result was generated by my PhD student Satyabroto, who is also having a poster in hall 3. Please have a look at it. And many of the idea that is initially started of dimensional reduction is started from one of my former postdoc, Navjit, who is right now a faculty in a state university. So I thank both of them. Most importantly, the resource that we generally get from our institute, the computing facility, has been instrumental to generate this particular work, and the funding came from our intramodal fund and the ACRB early KDR and core research grant. And finally, I'd like to thank the RARE. The past conferences has been truly intriguing to show us that there are different ways to think about collective variables. And I would like to also, even though I have not put the name, but I would like to really point out that two different persons' work, which is Andrew Ferguson and basically Protus Tiwari. These two persons' work has helped me to learn a lot about this idea of autoencoder and see whether one can think about and learn from this particular thing. So with that, I would like to thank all of you. And if you have any question, we can discuss.
Okay, thank you, Jagannath, for your great work. It's very interesting work. I see there are 2 questions in the chat box, so we'll take them first. The first one is from Tarok Karmakar. The question is, I guess the training data is from the unbiased simulations of the folded state. It's fascinating to see the autoencoder variables could capture or discover the intermediate states. I was wondering if they sample the folded and unfolded or misfolded states efficiently for a converged free energy surface. Are they biased simulations, simulation length?
Okay. I think that is a very important question. So basically, to tell you, the way we try to generate a free energy surface where you see folded state to have, let us say, having truly minimized, and the unbiased simulations, so the unfolded state is completely, let us say, in a maximized, mostly because what we did, we actually had a large replica exchange simulation as an input, and then what we did is that we tried to run many adaptive unbiased simulations by starting from those things. And essentially what we did is that we actually, when we got this, the two landscape Chi1 and Chi2, we tried to develop a Markov state model, and we tried to reweight each of the surface points by the stationary distribution that you get from those surfaces. So that way you can get the true weight that you basically are supposed to provide to the folded and unfolded state actually. So these are completely unbiased simulation, but they have been reweighted by the stationary population of each of those microstate that generally come from Markov state model.
All right. Okay. Thank you, Jagannath. The next one is from Pallav Datta. I am wondering, without having the concept of time lagging, these autoencoders are capturing slow collective variables. Can you please infer about why this might be happening?
Yeah, so this is a interesting question, because we do see that without even though in autoencoder, the one that we have basically generated here, it does not actually have any time lag time lag component, and still basically capturing the slow dimensions. It mostly, I think it mostly comes to the fact that mostly I think it can capture the non-linearity that is present in the data. So but you are right that if somebody actually try to look at a time lagged autoencoder and try to train the data, which we can, because we actually have the real time trajectories, maybe it can actually even give rise to better even better dimension reduction.
Okay, so I think we can take one more question. This one is from Anmal Kumar. The question is, if I understood it correctly, the neural network model or TICA are not reducing the number of collective variables, but just reweighting them. Will be better. Let me finish the last part of the question. Will be better to use a reduced number of collective variables for larger systems by applying PCA on reweighting CVs obtained from NN model.
No, I think just to be clear, I think TICA or the neural network, especially let us say if I talk about TICA, what you are going to get, let us say you have n number of input candidate CV. If you try to take a, if you try to generate a matrix from there, and if you try to take a projection, you will actually get n number of same number of TICA created dimensions. What we are doing is that out of, let us say, 5 Tika dimensions, we are choosing the top 2, which is supposed to be the slowest, and we are trying to project along those. Now, when it comes to neural network, the idea of neural network is that you are trying to not, you are not taking the input dimensions to project your data. You are slowly, you see the layers that you basically are forming, that is slowly reducing the number of nodes that you present there. So at the bottleneck, you are expecting that you will have only 2 to 3 maximum or 4. That is what you are expecting. So essentially, you are actually reducing the number of CVs actually there. So you have a very complex, function of the original inputs, which is present as a bottleneck layer, and that is along which you are basically trying to project your CV. So indeed, you reduce the number of dimensions there actually.
Okay, fine. Yeah, I think we are done with all the questions. I don't see any further questions. So let us thank Jagannath for this wonderful talk. Thank you, Jagannath.
Thank you very much.
With this, I think we are done with all the talks of this session. I thank all the speakers again for their wonderful talks and also for the discussions we had after each talk. And I thank all of you for attending the morning session. Before I close this session, I think Nishant would like to take a snap of all of us. We also need to send some snaps to IUSSTF, okay, the sponsor of this meeting. So may I request all of you to please switch on your videos so that Nishant can take a snap of all of us.
Thank you. Thank you. I'm taking, sorry, one more.
Yeah.
Okay. Thank you so much.
You're done, Nishant?
Yeah, I'm done.
Okay, great. Thank you again. Thank you for attending the first session of the meeting. The next session will start at 7:25 p.m. India time. So please join us back at 7:20 p.m. India time tonight. Okay. Yeah. Thank you again. Nishant, do you have any announcement to make?
No, Amalendu, thank you so much for chairing, and yeah, it's really perfect on time.
Right. Yeah.
We'll be posting the recorded videos on YouTube channel, and that will be shared on the Twitter page. The Twitter page is in the chat box, and it was also sent to you. So there, the videos will be available later today, actually.
Okay, fine. Okay, thank you, and thank you all, and see you in the evening India time, morning US time. Yeah, see you.
Right. Bye.